Welcome, everyone. This is a terrific turnout. It's great to see so many people here. I thought we'd go around the room and do no, just kidding. No, it's really a privilege and a pleasure to kind of kick things off and introduce this 50th birthday or anniversary celebration for the Institute for Geophysics. And as we'll hear from Jamie and Ian first, I'm not going to take too much of your time here, but one of the things that was exciting to me in coming here, that drew me to UT and to the Institute, is that the Institute has really been at the forefront of a lot of major discoveries. And the mission statement for the Institute is to conduct expeditionary research to understand how worlds work. And by worlds, of course, that means our planet, but as you'll hear over the course of today, also other planets. I guess another part of this that to me is really inspiring, and that I hope you'll join me in appreciating, and we'll hear a little bit about this from Ian and Jamie, is that this long legacy of discovery at the Institute began at a time when geophysics was very different and really in the midst of some paradigm shifting kinds of discoveries. So, for example, the Apollo mission had only recently returned samples. The ocean drilling program was in its earliest days. Plate tectonics was still kind of a nascent idea model that was being continued to be developed and proven through techniques like marine seismic reflection work, and the Institute played a huge part in that, and in fact in all of those. And over the course of the last 50 years, I hope what you'll appreciate from the presentation from Jamie and Ian in a moment, and also the series of speakers that we have lined up, is that the scientists at the Institute, and by scientists I mean our research staff, our postdocs, and our graduate students collectively, those are all the scientists, right? It's not just the PIs, have really played a major role in driving the way that geophysics is done nationally and globally. And what I mean by that is in playing a major role in, for example, advancing techniques in subsurface imaging that play into marine seismic reflection imaging, that again fed into questions related to the origin of ocean plates and the fate of ocean plates at subduction zones, driving the science in terms of how oceans and climate are connected, in terms of the search for habitable worlds, in the understanding and planning for an energy transition and carbon cycling from the seafloor to the oceans to the atmosphere. And the list goes on. And so really it's a celebration of legacy and also a little bit of a look forward. So today you're going to hear from Jamie and Ian with a bit of a retrospective or perspective on where the Institute has been, and in particular, some of those major accomplishments and a little bit of the history of the Institute itself. From there, we'll have a series of really exciting shorter talks focused on kind of emerging directions in the science that span from the study of major earthquakes and subduction zones to the search for habitable planets, to sea level rise, the fate of ice sheets, to imaging of offshore water resources using new methods. And then from there, of course, we'll retire to the lobby. Hopefully everybody saw that was set up for a reception with some student posters. So with that, I again, welcome everyone and invite you to join me in celebrating 50 years, which, just make a quick note, that is, I'm not going to be too specific, but that is longer than I've been alive and a smaller amount of time than our next two speakers have been alive.
Good afternoon, everybody. Well, I can only echo Damian's words that it's a privilege and a pleasure both to be here today, and to give you a little bit of background to the start of the Institute. And it's also a privilege and a pleasure to share this spot with my good friend and colleague, Jamie Austin. We've been around a long time together, longer than either of us like to think, I guess. But as you see, Jamie has been here longer than I have. But I'm getting the start because I'm going to talk more or less about what you might call conception and gestation of the Institute, while Jamie's going to take over at its birth and youth and go from there. What I mean by that is that I happened to be in Columbia University from the late 60s to the mid 80s when I came to UTIG. And at that time, the director of Lamont Doherty Geological Observatory, as it then was Maurice Ewing, who, of course, as you'll be aware, became the founding director of UTIG. And I know a little bit about how your doc came to leave Columbia and come here, because I happened to be chairman of the geology department in Columbia at the time. So I knew a little bit of the back channel to what was going on. Doc was the founding director of Lamont, of course, back in the late 40s. And as Jamie has indicated there on the right, he was UTIG's first director, arrived in Galveston in 1972, where there was a building built and named in his honor, which still stands, as Jamie will show you later, adjacent to the dock space for shipping. The medical branch trustee, Truman Blocker, was his benefactor, brother, as Jamie points out, of Dan Blocker, made famous as Hoss on Bonanza. I don't think I ever saw that long-running TV series, although I was alive. And UTIG was initially called the Marine Biomedical Institute because it was part of the medical branch. I guess that was the part of the deal that was organized at the time. And it's a portrait of Doc later in his career. So all this started where the red star is on the top right, or not quite top, but on the right-hand side there, in Schermerhorn Hall in Columbia University in the Morningside Heights campus. Here, as most of you will recognize, looking upstream up the Hudson River. And the gold star is where Lamont Doherty Geological Observatory, now Earth Observatory, was founded. It was given to Columbia University by the Lamont family, just at the time that Doc Ewing was hired as the first geophysicist on the Columbia University Department of Geology staff. And there's Schermerhorn Hall. Above the door, it says, "For the advancement of natural science, speak to the earth and it shall teach thee." Although as Lamont grew, the Department of Geology and then Geological Sciences occupied less and less space there. I used to try and tease the pigeons that the psychologists were getting to count beans or something like that as I went into my office and confused them in their experiments. So it gradually grew further and further away from geological science, which was originally what it was. But at the time that Doc went there, as I said, the Lamont family donated the estate here on top of the Permian Palisades sill on the western side of the Hudson River, again looking north along the Hudson. And on the top left, you see a picture of Florence Lamont presenting the deeds of Lamont Estate to President Eisenhower of Columbia University, a position he held after the Second World War, and obviously before he became President of the United States. So we had the Lamont Geological Observatory becoming the Earth Observatory and associated now with Columbia's Earth Institute. And one of the reasons why when the estate was bequeathed to Columbia, they gave it to the Earth Sciences, was because Doc wanted to set up seismic stations. And the New York Underground running by the Morningside Heights campus wasn't the best background. They're having a quiet seismic station. And that's why Lamont Estate came to be in the possession of, so to speak, of the Earth Sciences. Doc wanted to study the ocean basins. I was told by him several times, usually when he had a glass or two of wine at a reception, how my predecessor as structural geology professor in Columbia, Walter Bucher, Doc said he'd gone to Walter when he first arrived in Columbia and said, "What should I study?" And according to Doc Ewing, Booker said to him, "The ocean basins, my boy, that's where the answer lies." And that colored, obviously, the work that Ewing did. He got hold of a ship eventually called was called the Hazar, was renamed the Vima, and was operated there, as you see, as Lamont's flagship from 53 to 81. There's a story that Doc tried very hard to find somebody to give him a ship. He had one offer from somebody in New Jersey, but it turned out to be the chief of the local mafia who wanted a good connection with a reliable institution like Columbia. So he turned that one down, but eventually accepted the offer of the Norwegian shipping magnate, Vetlesen, of the yacht Hazar, which became the Vima, and it still sails as the Mandalay, as a tourist yacht, tall ship in the Caribbean, back to her sailing days. This map shows the 1,225,000 nautical miles sailed by the Vima in pursuit of science. It was, of course, the fact that Maurice Ewing put every instrument over the side that he could, including dragging magnetometers behind on all these trails, all these cruise tracks, that eventually led to the marine magnetic anomaly study of seafloor spreading. For many years, they published papers on the magnetics, but at least to this young structural geologist, they never meant very much until Vine and Matthews came along with the idea of seafloor spreading. And then suddenly, Lamont was sitting on a gold mine of data collected over years just because Doc Ewing wanted to measure something. Vima flew under the crown flag of Columbia. You may not be aware that Columbia College, University is Central College. Columbia College was originally King's College before the Revolution. And so it was probably the only US institution that flies a crown on its ships. However, as we move towards UTIG, in the late 60s, early 70s, Doc Ewing was approaching the age at which, in those days, a professor had to retire. And he wanted to stay as director of Lamont, even though he was going to be forced to retire as a tenured professor. But as I understand it, he had been such a thorn in the side of the Columbia administration for many years because of fights over money, essentially. The Lamont endowment and how that was going to, it was been given to Columbia on the understanding that they wouldn't take money away from the geology department because Lamont had money. But that, as I found in my years in Wisconsin, Columbia, and University of Texas, when you have some institution that's rather heavily endowed within the university, the administration is always going to try and take money away from you. And so that was why Doc was a thorn in the flesh of the administration in Low Library in the bottom right corner there, the main administrative institute of building of Columbia University on the Morningside Heights campus. So Doc had to leave, and he negotiated, as I touched on, and Jamie will follow up with some more on that topic. He had to leave and was able to arrange to go back to his original Texas roots and get some support to start UTIG. As I encroach a little bit on the time of Jamie, Jamie's going to be talking about in the early 70s, because Doc came in 1972 and died in 1974. I will go into 74. Oh, I seriously forgot to mention that not only did Doc bring marine geophysics to UTIG, but also, of course, the Apollo program through Yoshio Nakamura and others. So marine geophysics and lunar science were the two main fields that came with him to start up UTIG. It was in 1974 that I was co-chief scientist on the Glomar Challenger with my good friend, the late Peter Barker. And we were drilling on the eastern tip of the Falkland Malvinas Plateau at the black dot there, DSDP site 330. And we heard that Maurice Ewing had died while we were busy drilling there. And drilling, incidentally, he might have been chagrined into continental crust, not oceanic crust. But he'd done a lot of his original marine geophysics with Argentine scientists in the far South Atlantic and into the Scotia Sea, which is why I was lured to Colombia, because I was interested in that. And so we thought it would be very appropriate to name the bank on which we were drilling at the time he died, the Maurice Ewing Bank. That was breaking tradition and protocol, because you're not supposed to name features in the ocean basin with 3 names. It should have been just the Ewing Bank. But his brother John, of course, was a celebrated geophysicist, marine geophysicist himself. So we were given dispensation to call it the Maurice Ewing Bank. And so with that, I will step away and let Jamie take it over to going back a couple of years to the inception of UTIG. And do emphasize, I'll leave the main questions perhaps till after Jamie's talk, but he wanted me to say that anybody who wants to pipe up with a question while he's talking, he'd be very happy to entertain. So Jamie, up to you.
Well, let me say, to give a talk like this with my colleague Ian DL is a privilege. To be here, to have worked in this place for 44 years is a privilege, and I hope to work here a few more, so we'll see how it goes. Unlike Ian had a distinguished career well underway when he showed up at the Institute in '85. I was a punk. I had gotten my PhD on December 19th, 1978, and went home to New York, had Christmas, and then I hopped in my little Toyota and I drove to Texas. I had spent my entire life in the Northeast, my entire educational career in Massachusetts, and here I was listening to Ku Klux Klan on the radio, driving to Texas. I arrived in Galveston between Thanksgiving and New Year's 1978. It was a cold, rainy night, and I looked around and I said, what am I doing here? But I'm still here. Somebody had told me that I would be here to give this talk at the 50th that night. I would have said, no way. Damien mentioned that the field has evolved. It's more fundamental than I can possibly tell you. When I showed up in Galveston, that's Maurice Ewing Hall. It was built by the UT Medical branch for the Marine Biomedical Institute. It's still there. I was working for Geoforce, and we were in Galveston this past summer, and so I walked up the Strand. That's the main Wall Street of Galveston. I wanted to see if the building was still there, still intact. It's not only still there, it's still being used, and it's still called Maurice Ewing Hall, although it's been completely taken over by UT Medical branch, and there's no way anybody at the medical branch knows who Maurice Ewing actually is. But it's still there. The difference is that that dock is still there, but the ships are not. When I showed up, I got my PhD at MIT Woods Hole. I spent 4.5 years at the Oceanographic Institution on Cape Cod. It was all about ships. It was all about going to sea. And the reason I came to the Institute was because at the time, the Institute had 2 ships. We had just gotten the Fred Moore from Mobil Oil. It was a party boat. I mean, it was a crew boat. It was a party boat. It was a crew boat. And but it had been modified by Mobil to do seismic exploration, primarily in the Gulf of Mexico. And we got it. It was a mess. I spent my first month in January and February of 1979 collecting the trash. We put in a winch. We put in a seismic streamer. We installed 4 big air guns. And then I spent 3 months in the South Atlantic. And is Tom Shipley here? Tom Shipley was in the lab. He was a graduate student of Doc's, one of Doc's last graduate students. He got his PhD at Rice. And he was also down in the South Atlantic, along with some other people at the time, Dick Buffler and others. And that was our big departure. The lab at that time was completely funded by the oil companies. We had a center that was primarily involved with processing multi-channel seismic data, not just for ourselves, but for companies. The Marine Geology and Geophysics group was being supported with large sums of money by companies. And I'll get into the transition in funding, but we weren't that worried about money. We were a field lab. We were far away from the main campus. We had ample dough. The third brother, Ian mentioned Doc Ewing and John Ewing, another celebrated geophysicist, but there was a third brother, Bob Ewing. Bob Ewing was our chief of operations at the lab, the Galveston Geophysics Lab, when I showed up in 1979. They all looked almost identical. And we had a second vessel, the Ida Green. The Ida Green was given to us by Cecil Green, a luminary. He was the guy that actually opened up for Gulf, Saudi Arabia, oil and gas. And we named the Ida Green for his wife. She was primarily doing, there's the seismic streamer on the stern, but we were primarily doing seismic refraction in the Gulf of Mexico. And those were the days where you could blow large explosive charges off in the Gulf of Mexico. Try doing that now. But I learned how to put large explosive charges together, throw them over the side, roll them over the side. These were 700-pound charges, and then hope that they got far enough away from the Ida Green so we didn't blow the ship up while we were doing refraction. And 3 months in the South Atlantic, we nearly drowned a couple of times. A ship nearly sank off South Africa, but this was a very different funding mechanism. We had gotten money to do site surveys for what was the deep sea drilling project, the first phase of scientific ocean drilling. So we spent 3 months down there with money from Joint Oceanographic Institutions Incorporated in Washington. It was a huge chunk of money. Ran the boat for 4 months. And so this was the beginning of what I'll call a sea change, to use the NSF term, of the way the Institute was running. It was our big expeditionary departure from local, from the Middle America Trench and the Pacific, the Gulf of Mexico. We were headed way south, far away. And I can answer questions about the 3 or 4 months I spent on the Fred Moore, but that's a different talk. Both ships were gone by the mid-'80s. Ships are really expensive. Both of these boats were already long in the tooth when we got them. Maintenance on vessels is extremely expensive. And we had to get rid of them. At the time, we thought that was the end of our expeditionary phase. We thought we would never do that again, but we had a couple of years of real insecurity. After Doc died, we had a whole series of directors, 5 directors in 7 years. Creighton Burke, who was a famous marine geologist, had authored a famous book on continental margins. That's why I came to the lab, because that's what I was doing. I had authored the only multi-channel seismic study that Woods Hole ever did for my PhD. But Creighton died of a heart attack very soon after Doc died. Then we had a series of scientists. Joe Orzel was Doc Ewing's right-hand guy, but he didn't believe in plate tectonics. So you could collect seismic data, but you couldn't talk about plate tectonics with Joe Orzel. So you had to be really careful. And that was one of the reasons we had a hard time going to the National Science Foundation for money, because they had a hard time believing that we would use the data to advance the science. We were still getting money from oil companies. Paul Donahoe was a guy that was involved in the original design of our ocean bottom seismometers. We're still using ocean bottom seismometers in our work. He was a genius, but a crummy director. And finally, a guy named Robbie Moore in 1980 and 81. And by this time, the Marine Biomedical Institute had become the Galveston Geophysics Lab and was part of what was called the Marine Science Institute. There's still an MSI in Port Aransas. We were part of the MSI apparatus. So Galveston Geophysics, MSI, and the central office where Robbie Moore lived was up here in Austin. None of us thought we would ever see Austin. We were field labs. We were there by design. We were far away. It was almost impossible to get students. It was almost impossible to hire new staff. People didn't want to come to Galveston. They didn't want to come to Port Aransas. It's still an issue. The good news is that we were off the central campus radar. I had gotten $750,000 from the oil companies to go do some work in the Bahamas in 1980. I got the check. I was very close to going down to the local bank in Galveston and putting the check in as a CD in my name. And you may not, those of you don't remember, but interest rates were really high. You know, I think I could have gotten 14% on that $715,000. And I seriously thought about endowing my own position forever. My starting salary, by the way, was $16,500. But here was the problem. The ships were losing money. We had something called the Fred Moore revolving account. It had to equal 0 at the end of each UT fiscal year, it never equaled zero. It was always red ink. We had crew, we had maintenance. Anybody who's ever dealt with ships knows that they're big red ink items. And red ink never looks good to any university administration. That got us in a lot of trouble. And as I've said, Galveston was not a big draw for scientific staff or students. It was far away, fascinating place. For those of you who haven't been down to Galveston, take a dose and go down there. It's fascinating. It was called the Wall Street of the Southwest after the Civil War. It was the big cotton transshipment point, and it was a huge part of the Texas economy for a long time. Now it's kind of tourism, and that's it. But we had a really important thing happen to us in 1981, 82. We had a really small staff. SHUOSHUO was around. He was doing lunar seismology. Cliff Froelich, is Cliff here? Cliff Froelich was doing earthquake seismology, and very capably, but we were still in Galveston. We had a hard time. Students, getting students, you guys have a hard, some of the students, we have some students in the audience, right? Students have a hard time coming up here from campus to Pickle. Think about what it was like to be a student and go down to Galveston for a couple of years. You know, very few courses, a lot of opportunity to look at data and work with good people, including me, but it was a really hard place to be. You were remote in the truest sense, but we were able to hire this guy. He had been my boss at the Woods Hole Oceanographic Institution, Art Maxwell. He was co-chief scientist of Blake 3, which proved pretty much in the South Atlantic that plate tectonics existed, those marine magnetic anomalies that Ian mentioned, that was coming together. We now knew that seafloor got older away from mid-ocean ridges. He was the original architect of this with another guy named Dick von Hertzen from Woods Hole. That was basically the only science he ever did. Art was an administrator, but he did wonderful things for us. We ceased to be part of the Marine Science Institute. We became the UT Institute for Geophysics. And as an organized research unit, we had a chunk of money from the state, direct. We weren't part of the Jackson School. We were on our own. We got $1 million from the state direct. We answered to the vice president for research directly. Art was good friends with that guy, and he helped us a lot. Mostly he helped us get out of Galveston. Although we had a great building. The Maurice Ewing Hall was a wonderful, wonderful building. And when we came up to Austin, we were in rental space for a long, long time, in space that wasn't remotely as good as our building in Galveston. Frankly, our building in Galveston is better than this one, but at least this is a university-owned facility. Art came into the lab, he said, who's writing grants to NSF? No one. Why? Because we have plenty of money from various sources, and why write competitive peer-reviewed grants when we're getting the money without it? He said, no, you will start writing grants to NSF. I got one of the first ones in 82, 3 years to go work in the North Atlantic, but we began to branch out. He realized if we're going to be competitive, if the lab's going to be competitive, we've got to start thinking differently. We can't just look at the Gulf. We can't just look at local problems. We've got to get into polar regions. Larry Lawver came in 85. I had never thought about going to work in the Antarctic until Ian came to me and said, hey, it's great. I've been there multiple times since. Aerogeophysics, Don Blankenship. Some people, the ones in parentheses, and I believe me, I'm not being inclusive here about everybody. I've missed names, my apologies. But we had Duncan Young, an enormous effort there, primarily in the Southern Hemisphere. Plate tectonics. You know, Joe Warzel was ridden out of town on a rail. That's another story I can talk about. But we started to catch up in our ability to think in the 20th century about problems. The plates program that was, again, funded by industry was an enormous underpinning of our sense of plate tectonics globally. We got into neotectonics in addition to earthquake seismology. Fred Taylor, who's right over there. I went out with Fred to the Western Pacific, and he's been studying neotectonics forever and still is. Take a bow, Fred. Come on. There he is. Not just Fred, but disciples of Fred, Judd Parton. Judd's here too. Global continental margin studies. That's why I came to the lab. That's why, and we're still doing it. Sea level history, descriptive stratigraphy, 2D and 3D seismic reflection. We have probably the largest single group of people doing that kind of work in the United States, if not the world. A lot of really good people, excepting me, of course, but Nathan Bangs, Gail Christensen, who's now off at NSF, Craig Fulthorpe, who is also in the audience. Craig, raise your hand and take a bow. There he is. John Goff, Sean Gulick, Harm Van Avondonk. We have got a lot of really, really good people, and we have been getting a big chunk of money to do marine geology and geophysics on continental margins around the world now for 4 decades. And then quantitative geophysics. Mernal Sen, Paul Staffa came in the 80s as well. One of the appeals of the Institute has been the linkage between data and the field for a long time. How to manipulate data creatively and effectively and use it for field studies. Mernal and Paul were fundamental for that. But Art started it all for 12 years. He came in, he brought us into the 20th century and said, brought us up to the main campus, even though we were in rental space forever, said, we've got to be part of the main campus or we can't thrive. We've got to have students, we've got to have faculty, we've got to be able to attract them, and Austin is the place to do that. We owe him a lot. He just died a couple of years ago at 94. He gave way to Paul Staffa. Paul, as I just mentioned, was a quantitative seismologist. We have to remember, ORU, as an ORU, this is prior to the Jackson School, we had a pipe into the state budget. It underpinned salaries, it underpinned research budgets. Everything we had was directly from the state. And unlike the Jackson School, no disrespect to our dean, our lines of communication are longer now and more complicated than they were then in terms of the money, in terms of being able to access the money. Even so, we couldn't get a permanent physical home. Here in Austin, we were in 3 different rental spaces over a decade and a half. That was always a bit of a problem, and it's always been a problem that we're out here at Pickle and the main campus and the Department of Geology is 7 miles away. That continues to be an issue, has been an issue for the Jackson School forever, and will continue to be an issue because centrally having people in the same room talking, whether we're in COVID space or not, is an important part of getting science done, right? UTIG was not running its own ships anymore, but we realized pretty effectively that we could use other vessels and write competitive proposals to use other people's ships. That was a pretty important challenge that we faced, and we realized we could solve that problem. And funding sources under Paul continued to diversify. With Art Maxwell, we had gone into NSF. I was funded with a group by the Office of Naval Research for 20 years. And we started to look at foundation support like the Vetlesen Foundation, which has funded a lot of research here. The late 70s, we didn't talk about climate. There was plenty of ice. We didn't talk about CO2. We weren't thinking about it very much. It wasn't a mainstream conversation. We were talking about exploration. But believe me, the mainstream conversations that were going on now and then were fundamentally different. We were looking to fund ourselves, we were looking to impress our peers, but we didn't have the societal push for some of these issues in the cryosphere and climate that we do now. They simply didn't exist. And we were smart people. It wasn't there, it wasn't important. Now it is, and that's a big change. And one of the morals of this story is that the Institute has changed with the landscape. And that's what keeps us going. We've been able to do that. Terry Quinn was our next director for the better part of 10 years. Terry left here to go to NSF. We have had a continuing linkage with NSF through time. It's a very good one. A growing emphasis with Terry on the cryosphere, Ginny and all of the related people that Ginny works with and others. A growing emphasis on climate. Charles Jackson was here for a long time, has left, but Yuko Okamura and KRISTA, a lot of people are thinking about climate now. And I think the pendulum has very much swung. When I was a young lad, marine geology and geophysics, plate tectonics was the paradigm. Understanding planet Earth was the paradigm. It is part of the paradigm now, but it's certainly not where most of the money is. Most of the money is in climate. Most of the money is in the changes that we are wreaking on the planet and increasingly beyond our planet. So we have some very capable people now here. Got a new Center for Planetary Habitability, courtesy of the work that Sean and company did on the Chicxulub impact crater. All of this is good, and it continues to show not just an expeditionary focus, but a light on your feetness that the Institute has shown through time, partially because we see it coming, and then we plan for it by getting new staff and thinking about things in different ways. And now we come to our illustrious current director. UTIG has been part of the Jackson School now for about 15 years. Good things and bad things. I mentioned longer lines of communication, more complexity, but also more resources, more money, certainly more visibility where the central campus is concerned. That's a good thing. But the key is that we've been able to evolve based on these societal challenges. That's what keeps us alive. It's why I think at 50, we'll get to be 100. Okay. I think self-analysis is playing a very important role under DEMIAN. At multiple retreats, we're thinking more as a group of people about what's important and why we're doing it. Oh, sorry. Yeah. We're thinking more about ourselves, how we relate to problems, how we interact by hiring, how we attract good students and postdocs for these problems. We're thinking about that a lot now. That didn't used to be true. We were pretty much solitons before, all of us working our own shops. Clearly, the ongoing pandemic was a hiccup. It changed the physicality of the lab for a couple of years. Harm and Nathan and I were about the only 3 staff that were coming up here on a regular basis, and we would wave each other in the hall for a couple of years. But we never lost an identity. Zoom is a wonderful thing. I don't think it replaces what we're doing right here, but it's there. And new hires, along with ongoing retirements, that's a part of any lab, but we've got a continuing cohort of top flight research people. And because we're in Austin, and because I think the Jackson School has increased our visibility across the country and the world, we're getting some of the best students in the world. Remember what I said about Galveston? It was hard to get students at all. We had some great ones, but they were expeditionary just to come to Galveston. Now we're really getting great students on a regular basis. Got a couple of clouds on the horizon. I'm almost done here. In terms of marine geology and geophysics, 24 is going to be an interesting year. Scientific ocean drilling, which has gone through multiple phases, is likely to end at the end of 2024. Jordy's resolution, which has been around, I took her to sea on her first expedition for the ocean drilling program in 1985. She's going to be gone almost certainly at the end of 24. And at the same time, the seismic vessel Marcus Lanxess, with Nathan and others have used, Sean's used it, I've used it, is also going to end its life. There is a plan to have her replaced, but the plan has no substance. So we are likely to be, at least in terms of the marine geology and geophysics world, in a less equipped state for expeditionary marine geology and geophysics than we've ever been. Doesn't mean that we won't mine data and continue to do new things. Thorsten's pushing a new initiative later this week. We're going to do important science, but we shouldn't kid ourselves. A new drill ship will cost $1 billion. A new seismic research vessel will cost a lot, $300 million, $400 million. These monies are not easy to get. These capabilities are not easy to replace, and we're looking at some challenges ahead. Having said that, UTIG is much more than the MG&G Center it was when I showed up in Galveston in the late 1970s. I think we are still an expeditionary lab. I think about expeditions all the time. Seismic science is what I do. It's what a number of us do, but MG&G is no longer the majority of the staff at the Institute for Geophysics. We do a lot of different things, a lot of different acquisition and processing systems with many national and international partners. And I need to stress that. We're not just a national lab. We've got, almost all of us have got international links, and we do that routinely now. And that's a wonderful improvement over what we've done in the past. And I think we've been disciplined and strategic over the last 5 decades in staying competitive. The nice thing about being a relatively small lab and being introspective to a degree is that we can look at ourselves and say, okay, what do we need to do to make things, to stay competitive? And we just had one of those retreats this past week. Okay, that's it. Thank you. Ian and I will take questions from anybody on any subject.
Well, I'm sure folks have questions for Jamie about maybe some of those cruises he mentioned. No. I think there's a microphone coming from behind you. So it's a UTIG tradition, is the foam box with the microphone in it that we throw to each other.
So Jamie, are you telling me that geosynclines are no longer a thing?
I would wager to say that there aren't very many people in this room that even know what a geosyncline is. But I mentioned it in my PhD thesis, which shows you where I am. Our thinking has evolved, and in every area, you know, and you're going to be listening to talks from a variety of different disciplines. I think that's the healthiest sign of this lab. We've got people that have stuck around a long time. They have evolved, but we've got great young people and wonderful students that are showing us the way now. And yes, geosynclines are no longer part of the day-to-day conversation. Thank God.
Thank you. I'm Malcolm Ross. I was a student here in 1983 to 1987. We heard a little bit of history of the way Jamie sees the world, and I think that's what you expect. Let me add a little maybe revisionist history. I was part of the program that he mentioned, plates. I thought it got a little bit of a short shrift, so I'll add a little bit of history there. It was originally called the Paleoceanographic Mapping Project, PUMP. I think it started about 83. It ran as plates until, is it still exist or? Yeah, it has a successor, a long-running program on essentially building the tools and collecting the data for plate tectonic modeling. We use that computer, that VAX 11780 in the department, to do supercomputer graphics related to plate tectonics originally. Chuck Denham, who was here, did Terra Mobilis, was the first implementation of plate tectonic modeling on a Macintosh. John Slater was critical in our work. And most important, I think, was Chris Scotese, whose name hasn't been mentioned here. He was the founder of a lot of that plate tectonic modeling. After I left here, I did a lot of consulting, and I saw a lot of the roots of that in the industry. And I knew places that kept Macintosh computers in the lab, the only one of them, and it was only there to run the plate tectonic modeling software that we had developed. We were doing paleoclimate modeling, by the way, in 1987. We were talking about CO2 in the atmosphere and so on. So that was early days, but we were talking about the Cretaceous mostly. But anyway, so I think that thread also runs as a foundational thing that impacted in the industry and worth mentioning. So. Absolutely. Malcolm's right. I think I said at the beginning that I would necessarily short shrifts of people. I did that not by design. There were many, many smart people working on problems, plates, and its surrounding programs. I didn't mention Slater. I didn't mention Chris Scotese. Chris Scotese went on to, where did he go? Where did he end up going? UT Arlington and then Chicago. And Chicago. He, a genius, really, and really worked hard on both the software and the imaging that allowed us to visualize plate tectonics on a sphere. So really important stuff.
So actually, Malcolm's mention of the supercomputer in the 1980s reminds me of another important thing I failed to mention, and it didn't really come up in your talk, Jamie, but you know, one of the exciting new directions has been the increasing use of high-level computation in almost every aspect of what the Institute does. And so, you know, part of that in the last year or so and looking forward is forging new partnerships with our neighbors at TAC, the Texas Advanced Computing Center. And so there is actually a direct line where we actually buy out computing hours for supercomputing time for PIs at the Institute to try pilot studies or to do high level, whether it's data analysis of huge data sets collected in earthquakes and seismic data, or if it's forward modeling of geodynamic problems like of the kind that say Torsten Becker does in his group. And then the other thing I was going to mention is more of a question for you, Jamie, but I don't know if you wanted to say anything about, you know, another kind of exciting direction, at least from my perspective, ties into a lot of these legacy strengths is this rapid response program. And so I don't know if folks in the room have heard about this. It's relatively nascent, but it's both a way to engage with some of our student training. And so a lot of our MG&G field course expeditions are actually used as the baseline data to then go back out in a very nimble way after events like hurricanes to assess in what we call rapid response. But it's now much broader than that. So Jamie, I don't know if you understand.
Well, I mean, I started an endowment for rapid response, which our esteemed development team is working to augment with my help. It was a way for us, it is a way for us being scientists, teams of scientists, technicians, and students, to get after it. If there's an eruption, if there's a hurricane, to get after it. A lot of understanding the impact of these events is looking at what we call ephemeral processes. What does a hurricane do to a beach, a coastal region? Some of those effects disappear with time pretty rapidly. The idea of rapid means get in there, do those measurements pretty quickly. We had a good team, John Goff and myself and students and some technicians went to the New York metropolitan area after Hurricane Sandy. So, and we drove a Suburban up there with Texas flags flying, you know, and you go up to the New York metropolitan area after a major cataclysm like that and, you know, wave the Texas flag, see what happens to you. Well, it was fabulous. People would come up to us, and we were working mostly in Western Long Island Sound, and we're just wonderfully impressed that we were coming up there to help them assess the damages from the storm. And it was a revelation to me. I think we all got a lot out of it. We were interviewed on National Public Radio, so we got some press as well. I think that's something else I think we're working hard on. I think Constantino, I think we realize that the science we're doing now has societal impact. Our link to society is much tighter than it was in the old days. And we understand that that needs to be expressed. We had some students with us, and they saw that firsthand. They saw the societal impact of what we were doing. They too were interacting with National Public Radio. What a great experience for a student in communication. And oh, by the way, I didn't mention, something else I didn't mention was everything related to JEDI, equity, diversity, inclusion, justice. That is a wonderful change, because that was not a conversation anyone was having in the 70s and 80s in the Institute in Galveston and in the early days here in Austin. And that's a wonderful, wonderful change in the business and in the relationships we have among ourselves. And I think that's a great thing. So. Throw that.
I'm no quarterback.
Throw that box at Thorsten. Nice job.
Right.
Our scientists are nimble. You may.
I just want to add something as a relative newcomer here. Jamie's absolutely right. This place is great. It has fantastic students, great colleagues, and it's very nimble in terms of adjusting to the new science. And a big part of that is our support staff, both administrative and technical. And that's really something that makes this place special. And I think we all realize that this is a lot to ask, right? To move stuff around and evolve skills and so on. And I think we have a great system for that. And that's really super, including, you know, moving from engineering to computational stuff, which is really at the forefront. And that's just awesome. And it's allowing us to do the science.
Everybody in this lab, when they open up a laptop or their desktop machine, should pray to the east and to Mark Wiederspan, who's in the back. And Mark Wiederspan, right. I was a first year man in Galveston, and a guy named Doug McCown, and there's another story which I can tell over a beer. Doug McCown and I said, we need some support, some technical support for some of the processing we're doing. And so we went over to the UT medical branch, found this guy doing a little programming in 1981. He came to us in early 82, has been with us ever since. And it's fair to say that all of us could go away. The one guy that is truly and completely indispensable here is Mark. Well, let me say again on behalf of Ian, what a pleasure it is to be in front of you. What a wonderful lab this is. For those of you who are relatively new students and so on, feel privileged. I was a student at Woods Hole Oceanographic, a bigger place where students were not as valued. And I think you're in a place where students are valued, where students are parts of teams from the get-go, and feel good about it, because that's a special environment. Thank you.
I guess I'll use this microphone. All right. Thanks, Jamie and Ian. And Torsten mentioned something. I think it's worth, this may be the only chance I have to do so, is to mention not just Mark, but the entire administrative and support staff here at the Institute. You know, everything from putting together this event to proposals that in some cases are incredibly complicated with their budgets and cost sharing. And then once we have a grant awarded, how that gets spent and keeping us basically out of jail in a sense, right? Or at least out of trouble. So I'd like to give a round of applause to our support staff. So we're going to move on to hear from, there are a series of 5 talks that are really mainly from some of our early career, or at least sort of earlier half of career investigators that in a sense, I think are nice highlights or vignettes of some of the really exciting new directions that the Institute is taking in research. And the first of those is going to be from SHUOSHUO Han, who's on her way up here now. And she's going to share with us some really cool new data collected off the Pacific Northwest. And so this is seismic reflection data that tell us about the subduction zone there and the implications for earthquake hazards.
Thanks for the opportunity to presenting my work at this great event, and nice to meet everyone. I'm SHUOSHUO Han. I'm a research associate at the Institute. I'm a marine geophysicist, and specifically I use active source seismic data to image the sediment, oceanic crust, and uppermost mantle beneath the ocean. All right, so today I will be telling you about a project that I'm co-leading to image the Cascadia subduction zone located off the Pacific Northwest coast. But before I do that, I want to say a few words about how I got to UTIG. All right, so when I was a graduate student of marine geophysics at Lamont Doherty Earth Observatory of Columbia University, I found that many of the papers that I read were written by scientists from UTIG. Those papers, they use beautiful 2D and 3D seismic data to reveal great details of the subsurface of different settings, from continental margins to subduction zones, from oceanic crust to impact craters. And many of these studies also integrate ocean drilling data, which I find to be a very powerful approach in interpreting seismic data. And I think these papers really greatly advanced our understanding of the geological history and also tectonic processes of the different geological settings. And then I was like, those are really neat work. And those people happen to be at the same place. So this is a great place to do a postdoc. So a few years later, with the GeoPrisms postdoc fellowship, I came here to work with Nathan Benz on different subduction zones. So here I have been exposed to exciting science and technology. And also I met great colleagues, mentors, friends, and I enjoyed working here. So I decided to stay on as a research associate after my postdoc ends. So now as a research associate, I built my own research program. I study subduction zones at Cascadia and Puerto Rico, offshore New Zealand, and also Mexico. So today I will be telling you about Cascadia. So by the way, when I put together this slide, I tried to position the figures at where the study areas are, but it has been not very easy because like you can see like the study area are not evenly distributed. The Pacific Ocean is more extensively studied than other places. So like there's such a crowd at the Pacific. So subduction zones, many of you in this room are very familiar with subduction zones. So subduction zones are where 2 continental plates, they converge and one plate just thrust underneath the other. So at these settings, they host profound geohazards. Let me try to like point to, so the greatest earthquakes occur on the contact of the 2 tectonic plates. And also the motion, like during an earthquake, can cause the uplift of the water column that can trigger great tsunamis. One of the major subduction zones in the US territory is the Cascadia subduction zone, and it extends over 1,000 kilometers from offshore Vancouver Island to northern California. And it is where the Fuca plate and the Explorer plate and the Gorda plate subduct beneath the North American plate. And this figure is showing the, press this button. This figure is showing the seismicity that we have seen, and the red dots are the seismicities we see in the oceanic plate, and the green dots are the seismicity on the upper plate. But you probably have seen that in this zone of the plate interface, where the two plates are in contact, the seismicity is very low. So this margin is unusually quiet. So does this mean it is less dangerous? The answer is no. So actually, from paleoseismic studies, we know that great earthquakes, like magnitude 8 or 9 earthquakes, have happened in this margin during the Holocene repeatedly. And the latest one occurred on January the 26th, 1700, and it resulted a tsunami that travels across the Pacific Ocean and were recorded in Japan. At that time, it's called by Japanese people an orphan tsunami, because they didn't find a local seismic source. They didn't know that the earthquake that generated this tsunami was actually on the other side of the ocean. So if a similar scale earthquake occur now, it may cause the damage that is similar to the 2011 Tohoku earthquake that we see. It caused the great ground shaking and also large tsunamis, a lot of damage and casualty. So as a marine geophysicist, we want to have a better understanding of the structure of this subduction zone in order to understand its potential for generating earthquakes and tsunamis. So this red squares, like it's showing you the area that we're imaging. So we want to first know, like, the seismogenic zone, what is the down-dip plate interface properties that can help us understand which part of the margin is generating the great earthquakes, what is the fault properties, and what are the structures, how it will respond during earthquakes. And also, there have been observations for this along strike variations for the megathrust slip properties, slip behaviors from the current locking status to past earthquake rupture patterns. There seems to be some boundaries and also some like patches for paleo rupture ruptures that we want to understand. Are there any systematic variations in the structure and properties of the incoming plate or overriding plate that can contribute to this along strike variation? So with those driving questions in mind, we went out to sea in the summer of 2021 to conduct this Cascadia seismic imaging experiment, KC21, on board the RV lenses. So it was a 41-day cruise, and we acquired seismic data along 19 dip lines and seven strike lines. So for those of you who are not very familiar with multi-channel seismic acquisition, the ship was towing an air gun array that we had an air gun array of the volume of 6,600 cubic inches. This big volume and also the well-tuned source ensured that the sound wave generated by this air gun array travels through the water column and the rock layers and then bounce back and be recorded excuse me, by the hydrophones along the streamer. That is, the yellow cable is what we call a streamer. So we have hydrophone arrays that can sense the pressure in the water column, and they grouped at 12.5 meters. So the total streamer length is 15 kilometers. It may not be very easy to picture in your mind how long 15 kilometers is. So 15 kilometers is 9.3 miles. And I found the other day, like if you drive from UTIG to the main campus of the Jackson School, it's about 9.2 miles, almost exactly at 15 kilometers. So you can think of like you're towing such a long streamer at sea. So this expedition is quite spectacular. Although we do not really see the streamer is towed about 12 meters below the sea surface, but we can see like the buoy like very far away. So besides the multi-channel seismic component, we also have two complementary programs. The OBSs were deployed on every other defense. So these will give us velocity information for the deeper part of the Earth. And also we had a land program, and they deployed over 700 land stations, and that can listen to the Landsat shots during our experiments. So we will have some repass that across the shoreline. So in this picture, this is our group picture for science party and technical staff at the end of the cruise. Everyone was smiling, but this cruise was definitely not the smoothest cruise that I had ever had. So 11 days into the cruise, we were on one of our strike lines. I believe it's this one. And the weather was not great. The sea was pretty rough. And around lunchtime, we saw from the monitor, on the monitor that monitors the streamer, a big spike in the tension. Means there was a lot of tension on the streamer. And then it went red. And after a few minutes of confusion, and we realized the streamer was broken off from the ship. And we quickly started to retrieve the streamer, and that is all we got. This is actually the stretch unit at the front of the streamer. Having only this means we lost all our 15 kilometers of streamer. I have sailed 4 times on this ship before this cruise, both for 2D and 3D acquisition. But that cruise was the first time I served as a co-chief scientist. And I was like, wow, boy, this is rough. A streamer broken off from the ship. But the thing is, like on the ship, we also had scientists and technicians who had over 20 years of experience in this business. They had not seen this either. So this, like the streamer broken off is really a rare event. So we couldn't, 4 times, not that, maybe like before the 20 years, like for people. Yeah. And so we couldn't stop the ship immediately because we need to first recover our air gun arrays. So we kept going for a couple of hours, then we turned around and tried to retrieve our streamer. Our streamer was at that time drifting towards the beach, and because of the currents. So the GPS on the tail buoy really saved us, because from the GPS we can locate the streamer. And so we always sped up and to chase our streamer. And when we were in the vicinity of the streamer, like people are starting to because it was very foggy, and we try to see this tiny little red flag on the tail buoy, and also some STDs, those balloons that try to bring the streamer to the sea surface to prevent it from sinking down to the seafloor. And so we use all human power on the ship, try to locate the streamer. And eventually we found it, and we grabbed it at the tail buoy and reeled it backwards and to our rail. And then we've recovered all 15 kilometer streamer, which was a miracle. It didn't break into pieces. It didn't tangle as a spaghetti. And we covered it in the entire whole piece. And so that was amazing. And then we kept going with our data acquisition. So we had another few more events in this cruise. And so as a PI team, I work with the technical staff, and also the Marine office at Lamont to kept revising our data acquisition plan. We went from plan A to plan B, and eventually I think we ended up at plan K. So I really learned a lot from this cruise, and I think for people like us who do field work, unexpected things could happen, and it's almost inevitably happen. And when it happened, we really need to face it, and with courage and perseverance, and also creativity to come up with different solutions and to work as a team. So I think that is probably also the beauty of the field work. So the data turned out to be great, despite all those challenges. And in the next 10 months, we worked with a geophysical processing company, Ion Geophysical, to process the data. And just a few months back, we got the final products, and that I will show you in a second. So this line is a line that offshore the mouth of the Columbia River, and this was at a major data gap along this margin. So from this, you can see this is an incoming sediment section. And this reflector is top of the oceanic crust, and this bright reflection is the bottom of the oceanic crust, the oceanic moho. And this is the outer wedge that is constructed through this accretion of the incoming sediment section and inner wedge and shelf. If we zoom in for the outer wedge part, you can see the really detailed structure for those sediment strata and the fold and thrust, and yeah, that we can interpret to characterize its deformation and also the evolution of the outer wedge. We're especially interested in the outer wedge because this part of the subduction zone, especially for Cascadia, that is a very hot subduction zone. Here is where the megathrust, the seismogenic zone likely extends all the way to the trench. So this part of the megathrust is probably seismogenic, and also the vergence of the faults that can tell us information about like when an earthquake happened, how it deforms, and what is the tsunamigenic potential for the margin. So this is a line from offshore Vancouver Island, where you can see like these are the faults, the disruption of the sediment sections that extends all the way to the top of the oceanic crust, meaning the entire sediment section is accreted with very little sediment subduction. So sediment subduction matters because like how much of the sediments are subducted, it influences how much water is going the water budget for the subduction zone, and also the directly influence the megathrust property and the slip behavior of the megathrust. So as you can see here, like there is very little sediment subduction and the faults are dipping seaward, and those are the landward, we call them landward vergent faults. And when we move south, like we can see that this line has those also landward vergent faults, and those faults extends pretty close to the top of the oceanic crust, indicating very little sediment subduction. But when we move further south to offshore Oregon, we will see that now the faults are dipping the other way. We call them the seaward vergent faults. And also they show into a décollement, a detachment fault that forms in the middle of the sediment section, which means about half of the sediments is subducting, whereas the other half, the upper half, is accreted to form the accretionary wedge. So if we look at all the lines, and this is a compilation for the observation for all the lines, and here the vertical axis is latitude, and this is the amount of sediment subduction. We can see that for offshore Vancouver Island, Washington, and Northern Oregon, there is minimal sediment subduction, but there is significant sediment subduction up to 2 kilometers near the deformation from offshore Central and Southern Oregon. And also the fault vergence in the Vancouver Island and Washington, these are mixed vergence or landward vergence, and in the off Central and Southern Oregon, they are dominantly seaward vergent. Another line of information we can get from the seismic data, especially with the help of the long streamer, is we can derive very accurate seismic velocity. And the seismic velocity tells us how fast the seismic wave travels through the rocks, and it tells us the rock property. So for sedimentary rocks, the seismic velocity, VP, is largely impacted by its porosity of the sediment rocks. So the porosity can be reduced either by vertical compaction, like in the sedimentary basin, or it can be when you have the compression from tectonic stress, like the horizontal compression, it can also reduce its porosity. So by subtracting a reference velocity that represents the case in the sedimentary basin, we can isolate those two effects. And for the residual velocity, we can see how the tectonic stress, the horizontal compression, come to play. The red color, the blue color is positive residual velocity, meaning the sediments are compacted more than it should be in the sedimentary basin, and the red color is under compacted sediments, which means it's less compacted than the case in the sedimentary basin. So we looked at all the lines from north to south, and we found this compression zone, the landward compression zone, that this is a deformation front, and this is part of the compression zone due to this tectonic compression. And So you can see that this line for Vancouver Island have a pretty narrow compression zone. I would say not too narrow, 20 kilometers. And then like when we go to offshore Washington and where the outer wedge is pretty wide, the entire outer wedge is in the compression. And then the inner wedge now is like, it's shown in the red color. It seems to be under compacted. But when we go further south, the outer wedge has little indication for compression. Almost the entire wedge seems to have lower residual velocity in comparison to the reference velocity, meaning they are under compacted. So if we measure the zone of landward compression zone along the entire margin, and that is what we see is it's pretty large. It varies with the width of this outer wedge, and it is the largest offshore Washington, and it's really minimal offshore Central and Southern Oregon. So that means the wedge here, for Vancouver Island and Washington, they're quite strong and quite wide, and that has implications for when an earthquake hit, how the wedge will like deform during the earthquake, whether it can move as a rigid body coherently that facilitated large rupture over long distance and all the way to the trench or otherwise. And so the wedge strength, it seems to have a large variation from north to south. So the third line of the information that we got is by looking at the deposit from the abyssal plain, and we found offshore Central and Southern Oregon, there are large landslide deposit as shown here. So this is a work done by my student, Charles Babendreher. So Charles have looked at those deposits and found like sometimes they have this chaotic appearance. Sometimes those landslide deposits are shown as those thrust and fold structure. And sometimes they are shown as this blocky structure. And he looked at all these dip lines and strike lines, and he identified 10 massive submarine landslide deposit offshore Central and Southern Oregon, and they are huge. And the largest one covers an area over 5,000 kilometers with an estimated volume of 1,400 cubic kilometers. So these are really large events that we're now trying to characterizing the deformation styles for each landslide events and estimate their age through stratigraphic analysis. So to summarize our preliminary findings, we seem to find like the new KC21 data reveals significant variation in outer wedge structure and strength along the Cascadia margin. And offshore Vancouver Island, Washington, and Northern Oregon, we see this dominant fault vergence of mixed or landward vergent faults. It also has strong outer wedge with little sediment subduction and no massive landslide deposit. But offshore Central and Southern Oregon, we see the faults are dominated by seaward vergence faults and a very weak outer wedge, thick sediment subduction, and numerous massive landslide deposits. So these data are still very new, and we are still thinking, trying to figure out the links between those different observations. So, and I also welcome your thoughts, your input to help us decipher these mysteries, why they're linked like this. So lastly, I want to acknowledge NSF and our KC21 collaborators, the very brave team of the MGL 2104 that acquired the data, and my students and postdoc and UTIG colleagues for helpful discussions. And lastly, I want to say happy birthday to UTIG. UTIG is a great institute. I'm really proud to be part of it, and I look forward to working with you all in the coming years to make it an even better place. Thank you.
First of all, I would like to start by saying that I'm very humbled and honored to give you guys a talk today. I just started last month, moving from Hawaii over here to establish a new lab, which is called the Ocean Lab, Ocean and Earth Electromagnetic Laboratory. And this talk will be slightly different to continue kind of the historical view that presented by Ian and Jamie. And because it's a new field coming into, or new capabilities coming into UTIG, I would like to do some overview, historical overview, and show you the potential of the methods and applications. So I hope by the end of this talk, you will know more about marine electromagnetic, at least as I do in general perspective. And you will realize that it's no longer a low resolution method. So after Jamie thanked his hero, Arthur Maxwell, I would like to thank my personal hero, James Clerk Maxwell, and also frequently my imaginary friend, that he's the one that realized through these elegant equations, Gauss, Faraday's and Ohm's law, what we all use today is electromagnetic waves. When you have a magnetic field, it's perpendicularly causes an electric field, which we all use in our modern life. And this is the fundamentals of what we took and kind of introduced it to the marine environment. So what is marine electromagnetic? Based on those Maxwell equations, we have methods that is divided to two sections. We have a passive way to image Earth and an active way to image Earth. Now, think of it, if you saw SHUOSHUO's talk before, that seismic is based on a wave equation, therefore it gives you good structural information about the Earth. CSEM and MT, those are two methods that if the Earth is a matrix, it tells you what is within that matrix. So it's very sensitive to porosity, temperature, and the volatile, because it looks at the matrix and the pore fluids together. So with the, that's the pointer, yeah. So with the passive magnetotelluric, what we call MT, it basically that method relies on natural changes in Earth magnetic field caused by solar wind. It interacts with Earth, and then we're measuring the response. So our source is unknown, but it's a method because it's coming from deep Earth that allows us to see deep into the Earth structure, roughly about 200 to 250 kilometers, slightly through to the upper mantle area. And we can record that with those CSEM or MT receivers. Now, as opposed to land, which you can only record either passive or active electromagnetic field, in the ocean with these instruments, we can record both of them simultaneously because they work on different frequencies. To make that more an active system, we use an electromagnetic source, a dipole. This is the one developed at Scripps, and we tow it 50 meter or 100 meter, depending on the topography. Above the seafloor, we energize Earth, and then we can record again the response of the electromagnetic, the secondary electromagnetic field, and that will give us higher resolution because we're inducing current that we know exactly its magnitude and phase. Now, as I said, because it's a diffusion equation, there was a large perspective in the scientific community, I would say seismic particularly, that EM is because it's a diffusing equation, it's a diffusive method, and therefore it's a low resolution kind of way to image Earth, sort of like gravity. But I hope to convince you otherwise by the end of this talk. And I will start with very flashy, one of the recent and most classic studies of that recently came out in 2019, a group from Norway, Johansson. What they did is basically use those two elements, both the passive, the MT, and the CSEM, the control, together in a joint. Where is my cursor? It's not here. they basically took all these two data set together and inverted them in a very highly used code, Mari2DM, which I'll speak about later, across the Muhan's Reach ultra slow spreading zone. And the nice thing, you can see that how it tracks the upwelling melt nicely from the younger kind of lithospheric crust to the older lithospheric crust, and also the LAB, the electrical LAB, they call it. And that goes nicely, ties nicely with the lithospheric cooling models. So this is our current kind of imaging that we can do from very deep to very shallow. And you can also see that they can see here the moho rising up all the way up in that region. But it took a while to get there. And continuing this historical, and it's a nice day, I think, a nice opportunity to show historical evolution of a field. It started basically the ideas of EM methods, or marine EM methods, started in 1968. That was one of the first paper by Peter Bannister, who proposed that we can take using electrical horizontal dipole, what you saw behind the tow system, and we can basically image some estimation of the conductivity of the seafloor and beneath it. That was kind of the first early work. There was a bit before, but this is one of the key papers. But the majority of the work of that field started at Scripps during the 60s, led by Chip Cox and his students that they worked together after, Jean Philot. They developed most of the what we know today as the magnetotelluric empty and controlled EM, which is CSCM methods. It started with two of them and propagated afterward. And this is how it looked like in the early days. It was messy. It was messy, a lot of wires, big instruments, a lot of cabling, a lot of dangerous manual working. And it was mostly aimed for seafloor geology, mid-ocean regions, partially funded by DARPA for seafloor communication, which, by the way, they're still funding it. There was a cruise last year about the same topic, yet to be successful. But this is how it looked like. And then the source came into play, the towed active source. So in the late 80s, Martin Sinaut, which was at Cambridge at that time, he developed the first flown based on the Scripps principles, but the first one that actually worked well to study mid-ocean regions. Actually, I was Martin's last student during my master before he retired at 2014. And then Sina, Lucy McGarry joined Martin Sina, and then the UK Electromagnetic group moved to Southampton and developed from there. So then there was the capability of flying above the seafloor and then recording it with the Scripps receivers. And this is just to show you the evolution of that field from the early 80s. And you can see there was very little players in that field, only two academic institutions, the Scripps and Southampton, which originated from Cambridge. And there was a lot of collaboration with industry, with Exxon and with Statoil and AOA. Two major dates in that evolution. November 2000, there was the first time there was an industrial kind of experiment in a known region of oil and gas in Angola made by Statoil. That experiment repeated by ExxonMobil in January 2002. And this is opened the entire Pandora box to that field. Why? Because both studies on a known discovery of oil and gas discover that little anomaly over here. What we can see is basically the amplitude response from the into, auto above the receivers, and you can see how it deviates from no reservoir to a reservoir when they knew there was a reservoir. And back then, there was no inversion model. There was just the amplitude response and phase, and you plot it against some half-space models, and you can see, oh, there is a change. Therefore, we have something there. And there was some success, and there was some failures, but this basically spawned the initiation in 2002. There was 3 major contractors formed: EMGS, Western Gecko, and ahead of myself. EMGS, Western Gecko, and OM, which OM was a spin out from the University of Southampton by Lucy McGregor, who later established rock solid images. By the leader company was EMGS, that also purposely built those large 3D CSM vessels. And then the ExxonMobil kind of experiment reached the front page of the Wall Street Journal in 2004, basically showing the idea, I'm always confused with the button, the experiment of Exxon offshore Angola, and that opened a large perspective to the field of imaging oil and gas with using CSEM. So there was a lot of, since then, a lot of commercial development of instruments, transmitters. This is EMGS and others. There's some Chinese developed a few instruments, and commercial receivers. That took off since that 2004. But then 2 things happened. There was a commercial decline in all development of those systems and the exploration. First, it was the Great Recession between 2007 and 2009, which substantially reduced all exploration. And then the Paris Agreement about climate, which kind of the coin has felt that oil and gas is no longer the future, that substantially lowered all the expenditure on developing new systems and oil exploration. So what do we have today in marine EM system? I will divide it to what do we have in the academia and what do we have in the industry. First of all, in the academia, we have 3 major players taking out institution. It's the Scripps institution, I mean governmental institution, Scripps institution, University of Southampton, and Geomar has some instruments. And as you can see with all the blues, the dominating institution is actually Scripps, that after Chip Cox, one of his students, or later on his successor, Professor Constable at Scripps, continued to develop those instruments from deep towed, seafloor receiver, deep towed towed receiver, and surface towed receiver. And when we have that, we can basically image throughout from the upper mantle all the way to the surface. So we have the seafloor receivers, which can give us from 200 kilometers to 10 kilometers using seafloor instruments. And then we can tow an array with a source and some receivers, towed receiver, and there is denser data and smaller offset. So it gives us high resolution in the first kilometer. And this is a new system recently developed in 2015 that we can also put that same system into the surface and image about 500 meters in high resolution. So you have a method that goes all the way from the upper mantle all the way to the surface. And that gives us a lot of flexibilities in terms of the topics that we can research. And you can see here the geological domains. We can study the LAB, subduction zone, transfer fault, spreading zone, submarine freshwater, CO2 leakage monitoring, minerals, and so on. And this is the environmental and social impacts of each one of them. So by combining the MT and CSEM together, we can study a large number of topics. What do we have in the industry? So most of the companies kind of faded out because of the shift from oil and gas. The major player today, it's Ocean Floor Geophysics, it's a Canadian company, and Electromagnetic Geoservices, EMGS, in Norway. So OFG recently developed technology, one of a kind in the world, that they do a lot of projects that you can see the electrodes are coupled into the frame of the AUV, and that is mostly used for mapping seabed minerals, hydrothermal venting, and shallow structure beneath the subsurface. And that was not kind of practical until recently with recent loggers and reducing of noise of the AUV itself and other technologies. But they also have a midwater CSEM towed receiver array system that was built and developed by PGS in order to go and revisit old oil fields, specifically in the north and in Norway, offshore Norway, the shallow ones, in order to image oil fields that kind of to produce more oil from that reservoir. Now, as you can see, this is a very large system. It's a 2D CSEM that was translated in a way to an EM method. So it has a large dipole of 800 meters, and then a receiver array of about 8.5 kilometers. So not as big as SHUOSHUO showed 15, but still very large system. And that showed a lot of success. As you can see here, all the red stuff, it's basically oil and gas, because the color scale in the industry is inverse to academic one, which means red is more resistive. So it did very well for a few years. And based on that system, recently, earlier this year, the other company, EMGS, basically developed the same kind of concept, more of the concept of the Scripps towed system, to do deep mineral exploration using a towed receiver array. So that was for oil and gas, and this was for aim for mineral seabed exploration. Now I want to go back to this one, OFG PGS1, that because of the shift from oil and because of COVID, that system became jobless. And therefore, with the new initiative, together in partnership with OFG, we're in the final stages or in the process of acquiring that system, and we're going to modify it. We're going to modify it in a way that we're going to make it leaner, smaller, and more usable to research vessels that we have in academia, to NSF vessels. But we're not going to have it only as an EM system. We're going to add another component here that's called Fresh Sense, and that will have a suite of sensors, so it can be an all-stop shop to image things like nearshore submarine freshwater, or in geological settings of CO2 or methane hydrate. Sorry. We can also map that region using that streamer and with the high accuracy of a USVL on top of that. And that gives us an operation of 500 meters beneath the seafloor, but with this kind of long array, about 2 kilometers, we can see 1 or 2 kilometers into the subsurface. So we basically framing it to something that is more impactful to the environment and the topics that are more relevant than to our current time. Moving on to talk about, okay, we have all those nice systems. What about modeling? How we model this data? And I'll show you some examples from major works and some of my work. And we're going to look at again, sorry, some 2D deterministic based on Occam inversions and stochastic Bayesian kind of approaches, and what do we have in terms of 3D modeling. So modeling of EM data was problematic or non-existent until roughly 10 years ago, when Carrie Key and colleagues developed what we call MARI2D EM, which is a finite element modeling code that is based on the Occam smooth non-unique inversion model that minimizes a cost function based on a misfit. Now, the greatness of this software, besides being publicly available, made by Carrie, is this. You can see here, when you have the previous inversion code, there was a structure kind of linearization or segmentation of the model parameters that didn't capture well the seafloor topography. But Mare, you can capture it with triangles and quadrilaterals, and with each iteration, it's zoom in, and it knows when there is jumps in the resistivity, it zoom in better and refine the mesh. So you can get more an accurate result, minimizing the misfit. So you can basically get any solution of arbitrary polygons, and you tested it in synthetic models. And that code basically did some major discoveries. The first time that an upwelling melt, or basically rising on the mid-ocean ridge at the East Pacific rise was imaged using only empty data. So you can see how well it resolved the upwelling melt and just beneath that ridge. That's it for seafloor spreading. What about subduction zone? Most of you are familiar with the Nicaragua's subduction zone. You can see here how nicely you can see the incoming plate. And as SHUOSHUO mentioned about the importance of fluid going into the subducting system because it's a lubricant. You can see here the subducted sediment. All those yellowish colors, it's conductive material, which means sediment with a lot of fluids. And it also can image that nicely bending faults, how they extend downward. And this was made with the CSCM data. Some example for my work in 2017 and 18. This is gas hydrate chimney offshore of Norway system. So this is also using Mare 2D, but it's not only by using which algorithm used, it's how you use it as well. So you can see at the top, this is one line. Basically, I'm showing that line that goes here. You can see at the top the inversion model. So blue is resistive and red is conductive. If I just invert the seafloor receiver data, I don't get that much of high resolution on the chimney structure of that gas hydrate. If I do the Vulcan data, I get some higher resolution. If I combine the two of them together, I get a nice structure of that pipe chimney. And if I had seismic constraint from the reflection data and velocity model, you can see that it's pretty much the key thing here is that those two images of that chimney structure is very similar. So we reach to that high resolution vertical representation of that chimney without any seismic. Or with the seismic, you get very similar results. So that's already tells us, yeah, we can have high resolution imaging using EM. And last example, we did recently work at the Sleipner storage site for CSCM. And you can see here, we know that area based on seismic, that chimney site of the CO2, where there was injection of 2 weeks injection of CO2 in different saturation state, and we modeled that. But here I'm just going to show you the sensitivity studies, or basically the synthetic studies of that. And now we're getting some models of the actual data. So we did some synthetic studies based on that chimney structure, and we can see that's a true model on the left with 10% of CO2, and then below it with 20%. And 50%, and you can see how the inversion solves for that in the upper right for 10% less than what we had with the different porosities, but with an increasing of CO2 injection, we can have nice representation, and in 50%, it really resolved the true model. So that shows the capabilities of CSCM to monitor CO2 storage size, and here we only use 6 seafloor instruments. If we do it with a towed receiver, that will be much higher resolution and better method. Another method is the Bayesian modeling here that you can see. It's also developed recently and available. And if we compare between Occam, which is a linearized non-unique modeling, to the Gaussian Bayesian model, you can see in the black line, that's the Occam inversion, how it fits. And then the warmer colors show the higher probability. And then the red line as the boundaries of the Occam kind of estimates, and the white lines are the Bayesian estimates. So you might say, okay, the Occam is sitting really in the middle of that, but it's not normally the best case because it's ill-posed question, non-unique. So we don't have good constraint on the uncertainty. So if you can take that and you translate that to 2D model inversion, you can see the difference between the Bayesian and the Occam. So you can see the Occam shows you more kind of resistive structure, but that is not probably the ultimate representation of Earth. While when you have uncertainty of the Bayesian, that gives you maybe more accurate results of the subsurface. In terms of 3D modeling, this is where we struggle. We don't have much yet. There is the GoFam, which is developed at ETH by Gravier, but that's not publicly available. And soon we hopefully will have a Mari 3DM. Kerry is working on that, and that will be available as the 2D, and it will help us image places like the Hawaiian volcanic system with topography that is a struggle to do it with the 2D modeling. That's about it. I just want to finish with just showing you the video I took in that last cruise that we're mapping seafloor minerals. It's a collaboration between the Norwegian government, OFG, and Ocean Infinity. And you can see that, like, with that system, you send it for 24 hours, and we did three AUVs at the same time, and each one of them come back with about 70, 80 kilometers of data, 10 different data sets. So that gives you a large scale of data set, large mapping, and this is where I think the future is going. And a happy anniversary to UTIG.
Good afternoon, everyone. My name is Alejandro Cardona, and I am a postdoctoral fellow here at the Institute. And I am privileged to be here celebrating with all of you the 50th anniversary of UTIG. I think this is an opportunity to reflect about our past, but also it's an opportunity to imagine our future. And with that in mind, I have two goals for today. One, I want to show to all of you the capabilities that we have at the Institute to conduct expeditionary scale research related to methane hydrates. And two, I want to show to all of you the importance of geomaterial behavior for different geological processes related to methane hydrates. Now, let me start defining what are hydrates. And hydrates are these solid-like compounds that are composed of two major elements: a cage that is shown here on this cartoon, and within that cage there is a molecule that we call the guest molecule or the host. And in most geological environments, that host molecule is methane. So in the video you see here at the bottom left, that's an actual methane hydrate that is being dissociated. And as the methane leaves that cage, you see it is burning, right? It's releasing continuously, it's dissociating. And one of the remarkable properties of this compound is the ability to store methane. Volumetrically, 1 cubic meter of hydrate dissociates in roughly 170 cubic meters of gas. So this is a huge, huge volumetric expansion, and that's why we have interest in this for energy purposes, but also for the impact on climate and organic carbon cycles. And with all phase transitions or phase transformations, these molecules are happening in a certain space. And that space is shown here on the right. Methane hydrate lives at high pressure and low temperature. And that's limits the regions where we can find them naturally. And what are those regions? Here I'm pointing a map where each of these little markers represent a location where methane hydrate has either identified or it has been inferred to be there. And clearly they are everywhere, right? In fact, they host, the estimates, what we think they host 5 to 22% of organic carbon worldwide, right? They are primarily near continental margins because it's cold, because the pressure is high, right? In the deep sea, and because we have availability of methane. But we also have them in the permafrost, right? Where it's also cold. And here at our institute, we have focused recently in this little box here in the Gulf of Mexico. And as part of our project here, we have primarily focused on Green Canyon and Walker Ridge. But you may think hydrates is something new to the institute, and nothing could be farther from the truth. The fact is that hydrates has been, or the institute have a very long history of studying methane hydrates, starting in fact for the last 40 years. It started with Tom Shipley doing seismic analysis of detecting BSRs, but we have gradually transitioned throughout the years from that seismic perspective to creating a more holistic picture of methane hydrate systems, and now analyzing it in terms of modeling capabilities or in terms of experimental designs and so forth. And out of all these scientists that I have pointed out here, and I'm pretty sure I have missed a few, I want to highlight Tom Shipley. Why? Because he was one of the pioneers in the study of methane hydrates in the world. Tom was one of the first ones to identify the BSR, the bottom simulated reflectors in seismic images, and relate them to methane hydrates. So clearly pioneer studies have been come out of the Institute in a reflection of what my previous colleagues have said before. So now the history or the presence of UTIG is not only historical, it's also geographic. And in this map, what you are seeing is the same locations of methane hydrate that I have pointed out before, but now I have highlighted the ones where UTIG has, or where a UTIG scientist has studied them. So clearly, UTIG presence is not only historical, but also geographically. And we have not only focused on North America, we have a major worldwide presence, once again, in a reflection of what my colleagues have said before. Now, let me focus on the expeditions in the Gulf of Mexico. As part of this multi-year project, we went to the sea first in 2017, and part of the results that I will show to you today are samples of that expedition. But we also will go to the sea next year, and that's quite exciting. And the idea is to create this comprehensive view of methane hydrate systems, not only, again, from a field perspective, but also on a material perspective. Now, gas hydrate has been identified in the Gulf of Mexico since quite a long time. We was first identifying those seismic images in the identifying BSRs and doing geological interpretations. We have also identified them in the sea floor, right? But it all started, or it all took off with this joint industry project back in the 2000s. And this was the first offshore expedition intended to study methane hydrates in the Gulf of Mexico. But there was a caveat, or there is a caveat with these studies. And is that these studies focus on field-based analysis or well logging analysis. A missing component was there. And that component is the component that the current project is adding. It's adding the capabilities to add or to recover samples and be able to analyze them. Now, why we couldn't do that before? Because we didn't have the technology to do so. The UTIG project, GOM-Square project, is a reflection of all those years of development of these tools that allow us to recover methane hydrates. Now, you may think, why it's so complex to recover a sample? Well, because you need to keep the pressure and you need to keep them cold. Otherwise, that hydrate will be gone, right? And in addition to that, or what are the consequences of that? Better said. One, and this plot that you see here is showing that the methane that you recover at the surface will be gone by then. Imagine taking a sample out of the seafloor, taking it all the way to the surface, and as the sample goes up, it starts to bubble, it starts to dissociate. So all that methane will be gone. So with these capabilities, what we call pressure coring technology, we recover those samples with pressure, and we can carefully dissociate them in the lab so we know how much methane is there. In addition to that, the properties that we'll measure in the lab, if we don't do pressure cores, will be far from being representative. It will become like a mousse. So what you measure in the lab doesn't make any sense. So what with pressure core does is allows you to measure properties with the more intact samples, and that's something that is more representative of what is happening down there. And just again, to reiterate, the UTIG Square project tries to create this holistic, comprehensive view of a hydrate system, not only from seismic images and well-log images, but also with direct measurements, and trying to make that link between those scales. So broadly, what are the science objectives of this project? And we're looking this at two different scales. One at the reservoir scale, right, where we try to understand how the heat and water is transported through this system and how it eventually gets into the wellbore. But we are also looking at the more broad scale, where we are trying to understand how these systems are formed, how the methane is produced, how the microbes that live there produce this methane that eventually becomes hydrate, and how that methane is transported into these systems. And for all these two scales, clearly we need a proper characterization of the material and a proper understanding of this material. And I want to highlight something, and is that a big part of this project has been on the technology, because it's not only to recover those samples, and we have heavily involved in the development of these tools, but the sampling is just one part of the story. You need to be able to do tests with these samples, right? And in order to do those tests, you need to maintain the pressure all the time. So we at UT have developed this technology to store these samples with pressure, and to be able to cut these samples with pressure, right? And finally be able to analyze them. So it's a whole change of events that are important to recognize here. And we at UT have made significant improvements in that arena. And just to re-emphasize what it takes to make a measurement. We go to the sea, we go into a drilling rig, we take this sample that is stored here. We made a lot of effort to take that sample. We made some preliminary analysis at the dock, right, trying to get how much methane is there and so forth. And a subset of these samples, we take them to these vessels, we cut them and we put them into these vessels, we put them in this truck. And then we transport them all the way from the dock to UT. We keep them at UT in the lab to eventually make a test. So it's a long process to make a single test. So now more into the science component of this presentation. What I want to emphasize here is the geomechanical properties of this material, particularly the viscoplastic properties. And as the image that you see here on the right, things will deform with time if we wait long enough, right? And that's the idea of this concept of viscoplastic behavior. Oh, now let me just first define what do I mean by viscoplastic behavior, and I will do that with these simple examples. Imagine you have a sample here, and you don't allow that sample to deform sideways. You fix it sideways, and then you apply a force or a stress that is constant. You don't change it. You fix it. With time, what is going to happen? That the porosity won't change, right? The porosity will be constant with time. And the horizontal stress, the stress that allows this sample to maintain this uniaxial condition, won't change with time. In a different scenario, or in a similar scenario, imagine you have a sample and you change this, or you break it, but you break it at different strain rates. Once you break it fast, and once you break it slow. The strength of that material won't change, or will be the same regardless of the strain rate. That's more or less the concept of no time dependency. When we introduce strain rate dependency or time dependency into the system, and that's what we are seeing historically with methane hydrates, the porosity will decrease with time, the horizontal stress will increase, and the strength will be dependent on the strain rate. So clearly, we need to consider this when we talk about methane hydrates. And one way to test this hypothesis or to test these ideas is, again, running experiments. So what we do is we first identify which are the samples that have hydrate, and we do that in two ways. We first scan them in an X-ray that, again, needs to be done with pressure. So the vessel has to be pressure rated, and it has to be X-ray invisible, right? And we also measure the P waves. And those sections that have high P wave velocities are the ones that contain hydrate. And then we cut them, again, under pressure, and we put them into this device here. So a little bit of the results that we are seeing with this material, and a little bit of the test protocol that we have followed. All the tests start here, and you see different lines with different colors. The one that has hydrate, what we call a pressure core, is the blue one, and the other two are samples that do not have hydrate, right? And let's say we start here, we start to deform this sample. This is a strain versus a stress. We start to deform this sample, and at these discrete intervals, we hold the stress constant. We hold that axial stress constant. And what we're seeing here is that the sample is deforming quite significantly during those stress holds. And if you compare it with the hydrate-free sample, well, the sample without hydrate doesn't deform that much. So clearly the hydrate is promoting what we call this creep or time-dependent deformation at a constant stress. But it's also interesting to notice that if you look at the slopes of these curves, which reflect how stiff the material is, the pressure core is stiffer at these rates. So it's important to recognize that at these strain rates, hydrate increases the stiffness, but it also, when you hold the stresses, it promotes creep, which seems counterintuitive, but in reality is not. Now, what about the stresses, how the stress state evolved during those tests? And the color scheme here is the same, and what I'm plotting in the vertical axis is the ratio between the lateral stress to the axial stress, right? Is that ratio. So we first start at this point, and then we start to load the specimen. And when we do those stress holds, you see that this ratio goes up, meaning that this lateral stress is increasing with time, right? Which is, again, is in agreement with our previous idea or conceptual view of these systems. So as the material, as you hold this axial stress constant, the system is experiencing what we call a stress relaxation, stresses and relaxing. And as a consequence of that, the K naught goes up. This stress ratio goes up. Okay. And in the systems that do not have a hydrate, we don't see that behavior. So clearly, this is something that the hydrate is promoting or is causing. Now, this representation doesn't tell me anything about time, right? This way I'm plotting this data, right? So let's look at the time data. And here I'm plotting void ratio, which is just another way to plot porosity. And this void ratio is shown here in this blue, and the stress ratio, the ratio that I just showed to you, shown in red. So at the beginning of the test, you see, and this is log scale in the x-axis. So no, things are not changing that fast. It starts to accelerate and then it plateaus, right? And the stress ratio maintains constant. It's pretty much this in first 4 hours, right? And it starts to increase when you have seen a significant deformation in the sample. So the question is, why is that? Why you see us increasing the stress ratio after you have deformed the sample significantly? So our idea here is as follows, or model is as follows. First, the hydrate will bear that load, right? The hydrate here is shown in these green cartoons. The hydrate will bear that load and will start to viscously deform, right? It will start to push or expel water, right? That's the way these systems deform. And at this point, the hydrate has deformed that much that it doesn't have anywhere else to go. So the manifestation of the system when the hydrate doesn't have anywhere else to go is to increase the stress. The hydrate starts to push sideways, right? And that's how we interpret that this is happening. Now, this is nice, but we need to be able to translate these experimental results in some model that we can implement in a numerical simulator, let's say. So our first approach has been to use these spring and dashpot models, which are well known in the community to model these systems. And I think to a certain degree, this model capture this behavior. We see, or we are able to capture the decreasing porosity or void ratio, and we're also able to capture the increase in the stress ratio with time, with the caveat that we don't do that. We don't capture this mismatch in the time scales, or at least we're doing some first order approximation. Now, what are the implications of all this? Why do we care about this? And what are the implications of this small scale tests into a big geological system? And the way we saw, or the way we interpreted that is in two ways. Imagine you have a submarine landslide that is associated to methane hydrates. And one hypothesis has been that this landslide occurred because the hydrate is being dissociated, so the material loses its strength. Another possible hypothesis that doesn't require the dissociation of hydrate is that the hydrate facilitates this creep behavior. This slow movement is facilitated by the creep, by the hydrate, right? And that's just a hypothesis that we didn't come up with it, but it's something that our experimental results validate this hypothesis, roughly. And another implication of that is that systems in the subsurface that contain hydrate may exhibit high stresses, or in fact, they exhibit isotropic stresses, right? And the implications for that is that when we want to drill a well or we want to complete these systems, we will have a lot of problems, the same that we see in oil and gas when we try to drill through, let's say, salt formations, for example. And more broadly, I think with these viscous hydrate science that we are doing, we are trying to make some, or I'm trying to make some analogous to what UTIG is doing. And UTIG is studying glaciers, is doing these earthquake cycles with this viscoelastic component, convection, and I think it's all highly intertwined. And at the essence of that is this viscous behavior that I'm trying to emphasize here. Now, let me wrap up the presentation saying by UTIG has a long tradition of studying hydrate. This is not something new to us. And the GOM Square effort tried to provide a more comprehensive view of the hydrate system by combining different approaches. And for the science component, I think we must recognize the viscoplastic behavior of hydrate systems and the implications of that for different geological processes. And there are many people that have been involved in this research, and I'm missing a lot of faces, but I want to recognize the work of all these people. And finally, thank you very much. This sunset from the Gulf of Mexico, and I hope you like the presentation.
Thank you all very much for celebrating the anniversary of the Institute today. I'm really excited to be part of the Institute for more than 10 years, which amazes me to this day. So I started here in 2011 as a postdoctoral scientist, and I'm a research scientist now. So I had arrived here for about 2 days before I got on a plane and went to Antarctica for 3 months. So that is kind of what's shown in this first figure. And that was a really influential trip for me because it really started my path down planetary oceanography, where if you go to Antarctica, you have all of this like detailed appreciation of how ice and oceans can interact with each other. And that led me down the path of doing modeling of those activities on worlds beyond our own. And that's going to then propagate onto exploration of the solar system as well. And then I'll also talk about my other passion project of the ice giants and how we might be able to explore those in the coming decades. So just a brief introduction to icy ocean worlds. So these are growing in number across our solar system. And the most common icy ocean world is the Earth, but there's also quite a large number of ocean worlds going all the way from the asteroid belt, where there's the dwarf planet Ceres, all the way out to the dwarf planet Pluto, that's thought to also have an ocean that is then covered with ice. And in this talk, I'm going to be focusing on the Jovian satellite Europa for a number of reasons, but I'm also happy to talk about any of these other ones another time too. So to take a deeper peek at what is at Europa, this is just a schematic of what we think the interior of the satellite might look like. So that is the second satellite from Jupiter. So you have all of these radiation coming from the surface. And then the surface is basically a thick shell of ice that could be a few kilometers, it could be a few tens of kilometers. And below that global ice shell is a global liquid water salty ocean that's thought to be about 100 kilometers thick. And then below that is a rocky seafloor that's in direct contact with the ocean. And there's a lot of really exciting things that could be going on in the seafloor, such as hydrothermal vents that has big implications for the habitability of Europa. And the combination of all of these different aspects of the seafloor, the ocean, the ice shell, and even the radiation processing from Jupiter really make this one of the most exciting potential targets for life to be found in our solar system. So the aspect that I really think about in terms of planetary oceanography is how does the ocean move below the ice shell? And if you have all of this motion, how does that transport heat? How does that lead to material transport? And then how does that feed back into the habitability of Europa's ocean? But that's all well and good, but we'd really like to be able to test some of these ideas with future observations. So that's one of the second questions that I'll kind of address today. So the first part that I wanted to go into is just some basics about what we think the ocean circulation might be like at Europa. And I pretty much start almost all of my talks thinking about how fluid motions behave in planetary interiors with these very simple movies of creamer being poured into tanks of water that are or are not on rotating record players, because I think it really illustrates the possibility of flows that you might be able to see in an intuitive way. So the first one, you just have a stationary tank of water, you pour in creamer, it's more dense, it just sinks to the bottom and creates this like mushroom cloud type scenario. But if you instead rotate your tank, you have a really dramatically different fluid flow in this case, where instead of having that dense fluid kind of expand out on the bottom, instead stays really confined in this two-dimensional flow structure. So that's kind of just showing that because all of these ocean worlds rotate, it's going to have a really significant, or could have a really significant influence on what the ocean circulation could be like. And this is exactly, well, not exactly, but this is like kind of like the regime that the Earth's ocean is in. Okay, so those were really simple laboratory experiments, but you can also do much more complicated laboratory experiments, where in this case, it is a cylinder that is in a rotating table. It is heated from below and cooled from the top to drive thermal convection. And then it is rotated at different rates. So this case here is a case where it is rotating very quickly. So in that case, you have this really two-dimensional structure that you kind of saw in that record player experiment. And then as the rotational influence becomes weaker and weaker, you have basically this degradation of vertical flow structures as the rotational influence becomes weaker and weaker until it effectively acts as if there was no rotation at all. So we can do all kinds of like mathematical arguments, kind of using the foundations of rotating convection theory to make some predictions for where Europa's ocean might lie in terms of this relative influence of rotation. And I'll spare all the math for that, but the takeaway point is that we think Europa is in this regime where you don't necessarily have these two-dimensional flows, but instead you have this three-dimensional turbulence within Europa's ocean. And that's significant because it's historically always been assumed that Europa's ocean and the ocean of every ocean world basically behaves like this. So that's been kind of a change in how we think these oceans may behave. So to kind of build off of that idea and try to make them even more realistic, I've done some numerical simulations of rotating thermal convection in a thin spherical shell that is reminiscent of Europa's ocean. So this is basically just kind of shown in the schematic here, where you have a hot bottom boundary, you have a cold bottom boundary. It rotates at a fixed rate. We do lots of simplifications in terms of like not including any salt effects, not including any mechanical forcing, that type of thing. And we basically solved the system of Navier-Stokes equations using this open source model called MAGIC. So that's the kind of modeling that we do. And a lot of these runs are done on the TAC machines next door. So to just kind of give you some ideas of what the resulting ocean flows may look like, here I'm just going to show you three different types of outputs that we look at. The first one here are zonal flows. So these are basically just currents that are in the east or west direction that form. So if you have the blue colors, those are in the westward direction, the red colors are in the prograde direction. And in this case, you see that basically there's three zonal jets that develop with westward flow at the low latitudes and prograde flow at high latitudes. So that's just east and west, but you can also look at the radial upwelling and downwelling within the oceans as well. So in this middle plot, the red colors are radially upward flows, and the blue colors are radially downward flows. So you can basically see is that this sets up a type of like Hadley-like cell circulation pattern where you have upwelling and then downwelling, and that kind of has this global pattern associated with it. But we also want to think about heat is transferred in these models. So this last figure is basically just showing the evolution of the temperature field below, close to the top boundary of the model. And what you can really see is, well, one, you could see the direction of the zonal jets because you can see those patterns propagating. But more significantly is that you can see that you have more warm fluid impinging near the ice-ocean interface in these models at low latitudes with much less at high latitudes. So that's a really big indicator of how that might interact with the ice-ocean interface. But those models made one very big assumption, and that was that the heating from the seafloor is uniform in space. But that's really only applicable if it is due to radiogenic heating. But on all of these ocean worlds, there is a lot of tidal heating that happens because you're basically in kind of a non-perfect orbit around Jupiter. So the body flexes and heats its interior as it goes through the orbit. And that happens in a non-spatially homogeneous pattern. And what you instead get is if you include tidal heating, you get more heat coming out of the poles than you do at the equator. And you also have a longitudinal pattern that happens as well. But we don't really know how much tidal heating is compared to radiogenic heating. So what Daphne Lamascare, who's a postdoc who just finished with me, has been working on is trying to look at models that have a homogeneous seafloor heating. That's what's going to be shown on this set of figures. And then if you kind of increase your fraction of tidal heating compared to the homogeneous case to kind of look at how the pattern of seafloor heating affects your simulations. So that's kind of just showing as you go radiogenic dominated to tidal heating dominated. So what you can do from that is you can then see how this pattern of heating along the base of the ocean translates up to the ice-ocean interface. And the thing to notice is that there is a pretty strong translation of that seafloor heat flow pattern up to the ice-ocean interface. So that in and of itself is a really exciting result to us because that might allow you to then translate what you understand about the ice-ocean interface to the ocean seafloor interface as well. But we can go one step beyond that of making some substantial assumptions that simplify the ice shell. We can go take these spatial maps of heat flow to then make estimates of what the ice shell thickness as a function of space will look like at Europa. So we have these three different numerical models that you saw, and in this case, where you have the uniform basal heating, you have a much thinner ice shell at the equator than you do at the poles. But if you start to have a tidal heating pattern, you have a kind of a rather different scenario where you instead have much more longitudinal variability and you have local variations that can be quite strong in space. So that is one thing that we can use to then tie into observational tests of these ocean circulations. And then that leads into one of the upcoming missions to explore the Jovian moon Europa, and that is the Europa Clipper mission, which is the NASA flagship, which is the largest class planetary mission that NASA has. And this is to explore the habitability of Europa, or how suitable is Europa to potentially host life. It's not a life detector, but can it be suitable for life? So there's a large suite of instruments, including a suite of remote sensing across a wide range of different wavelengths. And I have the ice penetrating radar kind of highlighted here, because I'll talk more about that on the next slide. And that's significant because that is being led out of the Institute by Don Blankenship, who's the PI of this instrument. So we have a really central role in Europa Clipper in this reason instrument in particular. And in addition to these remote sensing suite, we also have a set of in situ suites that are a lot of different types of like mass spectrometers, and also things like magnetometers and plasma detectors and gravity and radio science to then complement this kind of remote sensing aspects. So as I mentioned, I wanted to briefly call out the REASON instrument, which stands for Radar for Europa Assessment and Sounding, Ocean to Near Surface. And I just wanted to highlight some of the specific hypotheses that we have designed the instrument to test. For example, that we've hypothesized that there are lenses of liquid water within the ice shell itself. And that's one of the things that we'll be able to test with this instrument. Also, that there is this global ocean beneath the ice shell, and this has some tidal flexing over time. So you're going to be able to see the ice shell move up and down by like 30 meters if there's a global ocean present. And then the final aspect is just that there's going to be a lot of exchange of materials from the atmosphere to the surface, within the ice shell, to the ocean, to the seafloor, and that all of that exchange of materials is really critical to the habitability of Europa. And by understanding what we know about the interior of the ice shell, we'll be able to see if there's any breakdowns in those exchange processes or not. And the figures, the people that I have down here are just, I'm hoping I didn't miss anyone, folks who are involved with the REASON instrument just at UTIG. We're a large team, both here and elsewhere. So I want to say these folks have been really awesome to work with. So this is just a schematic of what Europa Clipper looks like. So we have solar arrays for power. This big thing out here is the magnetometer boom. The REASON instrument has basically two parts. It has a VHF component, so that's these little parts here. And it also has an HF component, so that's what these antennas are here. And to give you a sense of scale, the Europa Clipper spacecraft is about as high as the Statue of Liberty, and to give you a concept of how big that is. So that's kind of just in schematic, but in real life, you can look at what the Europa Clipper spacecraft is doing. So this is an image from, I believe, yesterday of what the instrument actually, the mission actually looks like. So they have a live camera feed of the high bay where the spacecraft is being put together. So this right here is kind of the main body of the spacecraft. It's 10 feet tall by 5 feet wide. And then over on this side is the vault that protects a lot of the instruments from radiation. And then the spacecraft is intended to launch in October of 2024. And it will then insert itself into Jupiter's orbit in 2020 or 2030. So we have 6 years of cruise until we get there. And one of the unique things about this mission is that it's a multiple flyby configuration. So it doesn't go into orbit around Europa, it goes into orbit around Jupiter, and then does these multiple flybys of the satellite. And that leads to the coverage map that you can see on this kind of rotating Europa. So we're going to be in operation in the nominal mission for about 4 years and have something on the order of about 50 of these flybys. So I wanted to then change gears because I was very optimistic that I could get through a lot of material in 20 minutes when I gave my title in terms of planetary magnetic fields. So now we're going to switch, instead of thinking about icy ocean worlds, to ice giants, which are Uranus and Neptune. And that's because they have a lot of potential water, and at that distance out in the solar system, that would have been considered ices for astronomers. So one of the things to notice in this diagram showing the radial magnetic fields of planets with active magnetic fields at present day is that Mercury and Saturn look very similar, where they're dipole dominated and very axisymmetric. The Earth and Jupiter also look quite similar, where they're dipole dominated, but do have about a 10-degree tilt. But if you look at Uranus and Neptune, they are dramatically different, where they're not dipole dominated. The dipole that is present is not aligned with the rotation axis. It's instead dramatically tilted away. So the main question that I've been thinking about in terms of the ice giants is, why do they have these really unique magnetic fields, and what causes that to happen? So to do that, you have to understand a little bit more about what the interiors of Uranus and Neptune look like. And there's not a lot of constraints for this, because we're basically limited to data from one flyby of each Uranus and Neptune in the 1980s. That's all the information we have, which is for the interior at least. So it's thought that there's this outermost envelope of primarily molecular hydrogen, helium, and then these higher ices like methane and ammonia. Below that, the water that's present is under sufficient pressure that it can become ionized. So there's this ionic ocean below that. And then as you continue to go under higher and higher pressures, you can have this water then become super ionic. So in that case, it's thought that it could potentially be like a solid type of water again. And it's also not entirely known how much rock might be mixed in across all of these different layers. So there's a lot of uncertainty in what the interior looks like, but it's generally thought that convection in at least the Ionic Ocean and potentially down below can power a dynamo. So that basically converts kinetic energy into magnetic energy to create these magnetic fields. And the idea that we had is that one of the reason that you may have these multipolar magnetic fields is because you have interior that is dominated by this like three-dimensional convection that's not strongly organized by rotation, kind of similar to what we had argued for the Europa interior. And actually, this was where I got the idea for the Europa arguments. So we're basically going to argue that if you have this kind of messy internal convection, that will lead to a messy magnetic field. So we do some tests of that, again, using the same numerical code, looking at rotating thermal convection. And in this case, we've done two tests, one looking at a relatively thick geometry, and that's basically assuming that you have convection operating in both of these two regions. And then conversely, we have a similar one of a thin shell, where if you only have convection going on in your Ionic Ocean. And in both of these cases, we've designed our experiments to be in this kind of three-dimensional turbulence convective regime. And what we do is we kind of simulate what the magnetic field that would be generated from this type of convection that I'm not going to kind of show just for the sake of time, but the resulting magnetic fields are kind of shown here. So this intermediate plot is going to be shown at the full resolution of the model. So they can go up to like 200 spherical harmonic degrees. But the observations of the magnetic fields of Uranus and Neptune are really quite limited. So again, we just have one flyby of data. So we're limited to spherical harmonic degree 3. So that's, we know, the octopole, the quadrupole, and the dipole. So that's kind of what is shown in this one. And that shows that if you have a comparison against the similar spatial resolution to the observations, they look somewhat similar to what we observe on both Uranus and Neptune. So that is really encouraging and towards this hypothesis that this three-dimensional convective turbulence could be a reason for why Uranus and Neptune have these multipolar magnetic fields. If you do a similar type of argument for like strongly rotationally constrained convection, you generally get dipole-dominated magnetic fields, and that's the regime where you think Jupiter and Saturn might be. So that is consistent in terms of why we think Uranus and Neptune behave that way, but also why they are different compared to the other planets. And then the last aspect that I wanted to touch on was a recent mission concept that was recommended by the Planetary Science and Astrobiology Decadal Survey, which is the Uranus Orbiter and Probe, which is suggested to NASA and NSF that it be the next highest priority new flagship mission that goes into development at NASA. And that's really important because this decadal survey makes these recommendations, and then that gets relayed to Congress and funding bodies so that they can then hopefully move forward with a mission like this. And this is a really grand mission that would explore the entire system of Uranus. It would explore the planets itself, the rings, the moons, the magnetosphere, related to exoplanets, look at the heliosphere. So it's a really expansive project that looks at how the system originated, all of the different aspects in terms of how it works, including the magnetic field generation. The moons might have liquid water oceans within them. So that also has like habitability and astrobiology implications. And then, as I mentioned, it also links to exoplanets and heliophysics. So the nominal mission concept has a suite of instruments on the main spacecraft, but it also has an atmospheric probe that will then be deployed into the planet itself to understand more about what the interior is made out of. And the instrument that I'm particularly interested in, because I'm helping to put together an instrument proposal for this, is the magnetometer. So that will really be a way to kind of test some of these ideas about how the magnetic fields are generated. And then the last thing that I want to mention is like, what timescale might this happen on? So it was recommended that it would launch sometime in the early 2030s, and then it would arrive in the Uranus system in the 2040s, mid 2040s. So that's one of the reasons why I really hope that this gets started soon, so I will still be able to be part of it. And it's something that I'm really looking forward to in the next decades as part of UTIG having that part of it. Okay, that's it.
Thank you, everyone. I'm really pleased to be able to share with you my work today. My name is Benjamin KEISLING. I'm a research associate. I've been here since April, but time flies. And I've had a wonderful time at UTIG so far. I wanted to share a little bit to get started just about myself. I am born and raised in Portland, Oregon. I spent a lot of time growing up going to national parks or going to the beach with my family. I think that's one of the things that instilled an interest in the earth in me. You can also see that from an early age, orange has been one of my favorite colors. I think it's meaningful that I ended up at UT, although my hook'em horns were not fully developed then. I went on to a number of different places. Importantly, that journey has led me to a place where the main methods that I use in my research are numerical ice sheet models at different temporal and spatial scales, mostly continental scale. And importantly, in all the work that I do, I try to integrate those numerical models in novel way with different kinds of geologic archives. The themes that drive my research program are thinking about how ice sheets respond to climate change, in particular, what processes and mechanisms drove ice sheet change in the past, and then how can we use archives of past behavior, both to understand the present and to better predict the future. And I always get kind of philosophical on my birthdays, so forgive me, UTIG, for doing the same here. I love being an earth scientist. I think we live in a world where we tend to think of time as very linear, that there are some things that have happened in the past that led us to where we are today, that our decisions today uniquely determine what our future will look like. But as earth scientists, I think we're actually kind of liberated from that framework. We think a lot about how the past and the present and the future are interconnected. There's that famous adage, the present is the key to the past, but we also use ancient microfossils from ancient seas to help us understand what our oceans might look like in the future. We use observations from satellites high up in the atmosphere to calibrate models that are ultimately used to predict the fate of the planet. And so today I just want to share with you two kind of brief reflections on the ways that I've kind of used this framework to get at different questions related to earth science. So for the first part of my talk, I want to talk about a place that's called Camp Century, and indulge me. Could you raise your hand if you've heard of Camp Century? Fantastic, keep them up. Could one person tell me one thing that they know about Camp Century? What is it? Michaela? They found out that ice moves. Fantastic. So Camp Century is in Northwest Greenland. It was an early US military base during the Cold War that was originally intended as a sort of place where we could, a place that would be an early warning system if we were bombed. It was also intended that there were B bombs that stayed there that we could use to launch a counteroffensive. One of the first things that they realized when they drilled holes into the ice and started building railroads that were powered by nuclear reactors is that the ice actually flows under its own weight and it starts to close up. So ultimately, those military projects were abandoned, but it really advanced our understanding of glaciology, both in terms of ice flow, but also from the ice core that was drilled in 1966. We began to learn a lot more about the history of Earth's climate. A lot of the early studies by Willy Dansgaard and others on hydrogen and oxygen isotopes as a way to track changes in climate in the past came from this Camp Century ice core. One thing that a lot of people don't know, though, is that the ice core didn't stop when it hit the bottom of the ice. We actually penetrated about 4 meters of sediment beneath the ice core. And in 1972, those sediments were cut and put into storage. And then they were kind of lost for 50 years almost. They ended up eventually being moved to Copenhagen. They were stored in plastic bags and cookie jars at the back of a freezer in a sort of satellite facility of the University of Copenhagen. But in 2018, they were rediscovered, and it was realized by a joint team of US and European researchers that this could be a really rich archive of what happened before the Greenland ice sheet looks like it did today. Here's more of a timeline. But what I want to get into really is the results here. On the left-hand side is a description that we've made of this sediment core that comes from beneath the Camp Century site. We've identified 5 different units. The important thing actually is to note is that a number of these units are really rich with microfossils. There are abundant diatoms. There are different kinds of actual vegetation in the samples that indicate that when these sediments were laid down, this site was actually ice-free. And one of the things, today, the ice sheet at Camp Century is about 1,500 meters thick. So for the ice to be gone there implies that there would have been less ice in Greenland and therefore higher sea levels. But how much higher were the sea levels? One of the things we've struggled with in the modeling community is coming to a consensus on what Greenland looks like when it's smaller than it is today. And on the right here is kind of a survey of previously published efforts to look at different warm states of Greenland. And you can see that, so Camp Century is this, I should do it on the computer, but I'm not. Camp Century is up here in the northwest of Greenland, that red dot. And you can see in some of these simulations, Camp Century is uncovered, in others it's not. And we really wanted to come up with a way to answer that question of, if we know that this site is ice-free, what does it actually mean for sea level? And so in order to do that, we did a big ensemble approach to modeling this. I'm going to give you kind of the highlights, but happy to talk about more of the methods later. One of the reasons that we realized past simulations had shown a really big spread in what the ice sheet looks like is due to uncertainties in climatological parameters like temperature and precipitation, and also parameters related to the interaction between the ice sheet and the solid Earth, as well as the history of the ice sheet leading up to when it retreated. And so within our big simulation, what we were able to look at is what is sort of the range of states that the ice sheet could be if there was no ice at Camp Century, if we have that one piece of information. And what that allowed us to do is not put an exact number on how much Greenland would contribute to sea level if the ice sheet was ice-free, but we could put a minimum constraint on that. So what we found is within our entire library of simulations, we need at least 1.4 meters of sea level rise to come from Greenland in order for this site to be ice-free. Now, the number could be much higher than that. It could be 5 or 6 meters. And what we also see is that this site is not particularly good at tightly constraining how much higher sea level was when it was ice-free. And it sort of inspired us to ask the question, well, what sites might be better? So we've developed this methodology using an ensemble approach where we can really probe any site around Greenland within this ensemble and figure out where are locations where if we knew when that site was ice-free, we would have a very tight constraint on Greenland's past contribution to sea level. And what's beneficial about this approach is that in addition to finding places where ice-free conditions imply quite a tight distribution of contributions to sea level, we're also able to look within our ensemble and identify what are the parameters that really control that. So as we get new observations, we can know which of those observations are going to provide the most power to better constrain Greenland's contribution to sea level in the past. We've now sort of are using this methodology to look at the whole ice sheet and actually using it to guide efforts to look at for new archives. On the right-hand side is sort of a compilation of what this method allows us to do. It allows us to figure out for any given site, if there's no ice there, how much higher was sea level, and also how confident are we in that. And on the left-hand side here is a map from a publication earlier this year that we put out. We have a currently funded NSF project where we will be drilling through the northern Greenland ice sheet in 4 different places to obtain bedrock and actually provide a sort of fingerprint of when Greenland was smaller in different places. And this has been informed by a number of different data sets, including the radar stratigraphy, what we know about the temperature at the bed of the ice sheet, and also our modeling efforts. I want to also give a shout out to a couple of other kinds of archives and other kinds of projects that are getting at some of these same questions that I'm involved with here in UTIG. Recently, a team that I collaborate with was funded on a major new effort to look at all of the archival materials from all of the existing ice cores in Greenland. This is going to allow us to get really exciting new insights into these deeper parts of the ice sheet where the ice is very thick today, and find out when those sites were last ice-free to again use as a sort of fingerprint on the glaciological history of the ice sheet. That work is led by Dorte Dahl Jensen out of the University of Copenhagen. I also want to highlight work that's being led by Jenny Catania out of UTIG, which is looking at processes in a few glaciers in Northwest Greenland, and particularly processes of sedimentation, to understand how these, the way that glaciers bring sediment to their margins might provide a feedback that helps to stabilize them in the face of a changing climate. In particular, we're working with a number of different models to understand on what spatial and temporal scales might these processes serve as an effective feedback, stabilizing feedback. Another reason that we're interested in how glaciers will change with time is because as these glaciers change, global sea level goes up. Global sea level, however, is a issue that really results in profoundly local impacts. And so when it hits the coast, it interacts with a whole other host of Earth systems, an important one being structural racism. On the left-hand side here is a map showing that many of the US's coastal communities are more diverse than the national average. This has real impacts in many ways. When Hurricane Harvey hit the coast in 2017, one of the hardest hit neighborhoods was 49% non-white, much higher than the national average. This creates a challenge that the geosciences, I think, needs to answer in the next 50 years. You know, this work on the left, many of you have probably seen before, by 2 Jackson School graduates, Drs. Rachel Bernard and Dr. Emily Cooperdock, shows in black the number of PhDs in geoscience going to white people over the last 50 years, and in all of the other colors shows all of the other non-white groups. Over the last 50 years, there's been very little progress on a sort of demographic scale in addressing this injustice. I want to also highlight the work of Kailani Acosta, who's a PhD student at Lamont Doherty Earth Observatory, who has embarked and published a project on a sort of institutional scale survey of the dynamics there. And I think this is really critical as Earth scientists to think about how this planet that we actually all live on is one that everyone should have the ability to understand and access. And I guess seeing highlighted some of the people who've made really amazing contributions to our field over the last 50 years, you know, it makes you wonder what other contributions might we be missing because of the people that have been left out. And so this brings me to the second kind of archive that I want to talk about today. A quick show of hands again. How many people have heard of the first National Conference on Minority Participation in Earth Science and Mineral Engineering? Yeah, all right, a handful. I love to see that. This was a document that I uncovered in our archive in 2019. I know that it was presented to Congress back in 1974. But other than that, there's not much about it online. So if you know anything, let me know. It was organized by Dr. Randolph Brommery. It took place in Golden, Colorado. There were over 300 participants from more than 26 states. And this was a conference that was really focused on the barriers to participation for students of color in the geosciences back in 1972. Some of the document is really rich. I encourage everyone to read it. I think it's and in 1972, I want to highlight the year that UTIG was also founded and what we're celebrating today, which I think is really cool. I encourage everyone to look at it. There was a very diverse assemblage of people that were there. I think really importantly, a robust representation of people who represented the civil rights movement. And some of the things you learn when you look through that document is that what they were doing back in 1972 was thinking about connecting leadership at the chancellor level or even the governmental level all the way down to undergraduates, or thinking laterally, like connecting with religious groups. One of the things that's clear is that, you know, geoscience is done by geoscientists. The civil rights movement had a really important impact in this conference, and I think it's critical to think about what kind of social movements we are engaging in our work moving forward. And then also this idea that, you know, change just takes time. There were a lot of conversations that we have today were happening back in 1970. So it sort of calls that into question. And I have to say, when I first was engaging with this, I had sort of like an early career crisis. I don't know if you can say that, but as someone, I had a NSF fellowship for grad school, and the idea that broader impacts should be a really core part of what I was doing was something I took really seriously. And seeing how much had been done and then knowing that the impact had not been what people intended was actually like very kind of shocking to me. And what got me out of it actually was a colleague of mine saying, you know, it's not just that it doesn't matter that people have done it before and it didn't work. It doesn't mean that we can't make a difference in the future. It just means we have no choice left but to be brave. And so what we sort of did to try to think about that past, present, and future and how they interact, and to also have a sort of 50th birthday celebration happened in August of this year. We held the second national conference in Washington, D.C. Those are my colleagues, Dr. Raquel Bryant and Dr. Rachel Bernard, there at the conference. Just quickly, some of the key elements. We raised funding from NSF, but then a host of other sources, about $700,000 in total. It allowed us to have trained facilitators in every session, more than 200 people in person, 80 online. The first time AGU ever did a pay what you can registration model, which I'm trying to get them to implement across the board, but it's so far no dice. We had 5 different types of sessions. We really wanted to bring that sort of energy of engaging the civil rights movement and engaging with different ways of knowing into the conference space. And so we had a really diverse assemblage of different sessions that were actually participant driven. We used a sort of online pre-conference meeting to organize our sessions so that people could kind of shape what the conference would actually look like. And you can see all that online. So I will move forward and say that these 3 themes ran through the entire conference that really connect to what I started with, thinking about the archival, reading the past to create paths forward, the urgent, justice for geoscientists of color, and the imaginary, a radically different future. And so through this conference, we were able to achieve some of the goals that we had set out to, building communities and coalitions. There are actually a number of grants that are in progress of teams that just met up at the conference, which has been really cool to see. It was wonderful to celebrate our legacy in a similar way to what we're doing today, connecting people from different generations and making sure that cross-generational storytelling had a place to happen. You know, we can often think of this sort of no progress as meaning, well, you know, there's no one who has succeeded in the geoscientist who wasn't white, and that's just not true. There are so many people who have managed to really make a lot of contributions to geoscience despite huge barriers, and we wanted to make sure that that was really lifted up and celebrated. We had a lot of cool sessions. We created a radical earth learning environment is what we called it, but we had a lot of really yeah, challenging keynotes and session types that were very generative. And I encourage you to check out the keynotes online to learn more about that. And then finally, we're working with a team of scientists, humanists, and artists to create a sort of community-driven roadmap that's thinking 50 years into the future that we're calling the 2072 report. So we think about not repeating that those same dynamics again. And so I'll wrap up with just one last dip into the archive and thinking about our future. At the first national conference, in one of his keynotes, Bromry, who was the chancellor of UMass Amherst at the time, he shared an anecdote about how they had increased the number of Black students at UMass from a couple dozen to more than 1,000 in a way that also resulted in increased student success across the board for white students too. And what he shared after sharing that anecdote is that he said, we are convinced that we have demonstrated that a few people who work together and seriously want to make changes can succeed. He said that in 1972. And it just struck me as I was listening to the talks today, when I was listening to Jamie say, one of the things that's kept UTIG going is the ability to evolve, to meet new challenges. And as I hear my colleagues before kind of talk about what they're doing, groundbreaking methodologies, new archives, novel approaches, I think it's remarkable how much this resonates, and they're applying all of these things to our shared charge, understanding how worlds work. Our world is defined by a lot of big challenges. The profound geohazards, accelerating climate change, the search for life on other planets, the challenges of structural racism on our own. And I think that as Jamie and Ian said, and I won't be able to say it as eloquently as they have, in addition to this being a moment where we have a chance to reflect on our past and think about our present, I think this is also an opportunity to think about where we're going into the future. And as we've talked already a little bit about 50 years from now, UTIG would be 100 years old. I think imagining in the future, 50 years from now, what people will say then is kind of up to us. The grants that we get, the papers that we write, but also the questions that we ask, how we ask them, who we ask them with. And I think, as was demonstrated by all of the speakers before me, as you will see at the student posters later, as is in keeping with the legacy of this awesome institution, in order to rise to that responsibility, we have no choice left but to be brave. Happy birthday, UTIG.
Well, I'm not sure I could offer any closing remarks any better than those anyway. So I think the best thing to do is let's adjourn to the lobby for those who are interested. And there are a handful of student posters up, and there are some drinks and refreshments there. So thanks again, everyone, for coming and for joining in this celebration. To have a quick round of applause for everyone.